I was sitting in my car this morning, just dead stop in traffic, staring at the bumper in front of me.
Oh, the worst.
The absolute worst. And I had the radio on, it was mostly static, and I tried to send a text, and it wouldn't go through.
No signal.
No signal. And for just a split second, I felt this really distinct sense of isolation, like I was suddenly in a bubble.
It's a panic almost, isn't it? That feeling of being cut off.
It is. It's a sudden, sharp realization of how fragile our tether to reality, to each other, actually is. We spend our entire lives just assuming that if I speak, you hear me.
Right.
If I type something, you'll be able to read it. We just assume connection is the default state of being.
When it's actually the exception. It's the thing that has to be actively built.
Exactly. And that's why today we're doing something a little different on the deep dive. We're not looking at the history of the phone or the sociology of social media. We are stripping it all the way back.
We're going to the bedrock.
Yeah.
The absolute fundamentals.
We are talking about the physics of connection, the actual mechanical, invisible architecture that lets a thought in my head somehow, almost magically, teleport into yours.
Right?
And looking at the stack of research we have today, and we've got notes here on optics, on wave mechanics, biological evolution, it is so much messier and, frankly, more fascinating than I ever realized.
It really is. And you hit on something so important there. That feeling of isolation when the signal cuts out.
Yeah.
Because at a fundamental physical level, the universe is not built for connection.
What do you mean by that? I mean, I feel like everything is connected. We talk about the butterfly effect and all that.
Sure, on a cosmic scale.
Yeah.
But think about it on a human scale. You are a biological entity.
Yeah.
Your consciousness is encased in a skull.
Okay.
I am another entity.
Yeah.
Over here in a different skull.
Yeah.
There is no physical wire connecting our brains. My thoughts have no mass. They have no charge. I can't, take an idea out of my head and hand it to you like I can hand you a sandwich.
So, technically, by default, we should be trapped in our own heads, completely alone.
We are trapped unless, and this is the whole story of life and technology, unless we can solve the fundamental problem of physics. How do you transport something abstract, something with no substance, like information, across a physical gap?
And the answer?
The answer that nature came up with billions of years ago, and the very same one we use for Wi-Fi today, is energy conversion. You have to turn the idea into a thing.
This brings us right to the architecture of communication section in the notes. And I really want to spend some time here because I think it's something we all take for granted.
We absolutely do.
There's this 4-stage process laid out here: transduction, modulation, propagation, and reception.
It sounds like a really dry tech manual, but I promise you it's actually the story of how we escaped that isolation you felt in your car.
Okay, let's start with the first one. Transduction. It sounds like something out of Star Trek. Captain, initiate transduction.
Transducers to full power.
Yeah, it does sound dramatic, but all it means really is translation. It's the first step.
Translating what to what? Translating your abstract idea into a physical object that can travel, you have to turn your thought into a signal.
Okay, so right now, as I'm speaking, the thought is in my head and my voice is the signal.
Your voice is the start of the signal. But let's get even more fundamental. Forget the microphone for a second. You are pushing air from your lungs. That air is forced through your vocal cords, which vibrate.
Right.
You are creating a pressure wave in the air. You are physically battering the air molecules in front of your face, organizing them into a pattern that represents your words.
Which is kind of a violent way to put it. I'm battering air molecules.
Communication is a physical act. It's not abstract. Those battered air molecules then travel across the room and smash into the diaphragm of your microphone.
And the diaphragm is just a little membrane, like a tiny drum skin.
Exactly like a tiny drum skin.
Yeah.
It's a hypersensitive membrane. And this is where the real magic happens, the transduction. It's a process called electromagnetic induction.
I remember this from high school physics. Vaguely. It involves magnets and coils of wire.
That's the one. Attached to the back of that little diaphragm is a tiny coil of wire, and it's wrapped around a small, powerful magnet.
Okay.
When your voice, that pressure waves, pushes the diaphragm in, it physically shoves that coil of wire.
It moves it.
It moves it. And the universe has this very strict, non-negotiable rule. Whenever you move a conductor, like a copper wire, through a magnetic field, it forces the electrons inside that wire to move.
So my voice, the physical pressure of my breath, is literally shoving electrons down a copper wire.
Precisely. You are converting mechanical energy, the energy of moving air, into electrical energy, the energy of moving electrons or current.
Wow.
And the beauty of it is it's a perfect mimic. It's a perfect translation. If you shout into the microphone, you shove the diaphragm harder, the coil moves more, and more electrons flow. That creates a higher voltage.
And if I whisper?
You barely move the diaphragm. Fewer electrons flow, a lower voltage. If you sing a high note, the pressure waves are fast, the diaphragm vibrates back and forth quickly, and the electrons wiggle back and forth in the wire at that exact same speed.
So the electricity is my voice. It's not just a symbol of it. It's a literal physical map of the sound.
It's an analog, a continuous flowing copy in a different medium. But now we have a big problem.
Okay.
Electricity is great, but it's stuck in a wire. What if I want to talk to someone in Tokyo or broadcast to 1 million people at once? I can't run a dedicated wire from this studio to every single listener's house.
I mean, we used to, right? The telegraph system was basically that, but it's incredibly inefficient for, talking to a lot of people at once.
Exactly. We want to send this signal wirelessly, through the air, through the vacuum of space even. But you can't just throw electricity into the air. It doesn't fly.
So we need a vehicle.
We need a mule.
Yeah.
We need something to carry the signal. And this brings us to stage 2, modulation. This, to me, is one of the most ingenious concepts humans have ever figured out.
The source material here uses a great term for this. It talks about the carrier wave. I love this concept.
It's a perfect name for it. Imagine a radio station, let's say 101.5 FM. In their broadcast tower, they have a machine that does one thing and one thing only.
What's that?
It generates a pure, simple, dumb electromagnetic wave that oscillates at exactly 101.5 million cycles per second.
Okay.
It never changes. It carries absolutely no information.
Yeah.
It's just a steady, predictable hum flying out in all directions at the speed of light.
Yeah.
It is a blank canvas.
It's the highway, but there are no cars on it yet.
That's a great analogy. It's a perfectly paved, empty road to everywhere. So now we have two things. We have your voice signal, that electrical mimic we just made in the microphone.
The cargo.
And we have this blank carrier wave, the vehicle. We need to strap your voice onto that carrier. That process is modulation. We have to change the carrier wave in a systematic way that represents your voice.
And there are a couple of main ways to do this that everyone recognizes from their car dashboard, AM and FM.
Amplitude modulation and frequency modulation.
I feel like most people know the acronyms, but if you actually ask them what is physically happening to that radio wave, they'd be completely stumped.
Let's break down AM first. Okay, so amplitude modulation. Amplitude is just a scientific word for strength or height, how tall the wave is from its center line to its peak.
So in AM radio, we take that steady, boring carrier wave,
and we change its height, its amplitude, to perfectly match the voltage of your voice signal.
So if I scream into the mic, creating that high voltage,
The carrier wave gets huge. The peaks become mountains.
and if I whisper, the voltage drops.
The carrier wave shrinks down to a tiny ripple. The crucial thing to remember here is that the frequency, how fast the wave is vibrating back and forth, never ever changes. The distance between the peaks is always identical, but the peaks themselves are constantly growing and shrinking in time with your voice.
It's like using smoke signals where the puffs are always exactly 10 seconds apart, but a big puff of smoke means danger, and a small puff means hello.
That's a very good way to think about it. The information is in the size of the puff. But there is a massive inherent flaw in AM. And it's the reason your AM radio sounds like absolute garbage during a thunderstorm.
Yeah, I read about this in the notes. It's about noise susceptibility. But why is AM worse than FM? What is it about lightning that specifically hates AM radio?
Well, think about what lightning is. It's a massive, chaotic discharge of electromagnetic energy, a giant spark. In radio terms, that spark is a huge, unpredictable spike in amplitude. It creates a surge of voltage in the air.
Okay, I think I see where this is going.
If your little radio receiver is sitting there, and its job is to understand the music by reading the height of the incoming waves, and suddenly a lightning bolt adds a massive random spike of height to that wave.
The radio thinks the lightning is part of the song.
And has no way to tell the difference. It just sees a giant peak in amplitude and interprets it as a really, really loud drum beat or a cymbal crash. That's the crackle you hear.
So any random energy interference in the atmosphere, a blender motor, a power line, lightning, it all shows up as amplitude spikes.
Most of it does, yes. So AM is inherently dirty. It's susceptible to noise because the information is stored in the very property that is easiest for nature to corrupt.
Which brings us to FM frequency modulation. This feels like the smarter, more elegant cousin.
It is the more robust cousin, for sure. It's an ingenious solution to the noise problem.
Yeah.
In FM, we look at that carrier wave and we make a rule. We are never, ever going to touch the height. The amplitude is locked. It is full power all the time.
So the signal isn't getting louder or quieter. How do you hide the information in it then?
We wiggle the timing. We modulate the frequency. If your voice goes up to a high pitch, which is a high-frequency sound wave, we squish the carrier waves closer together. We increase the radio wave's frequency.
So it vibrates faster?
It vibrates faster. And if your voice goes down to a low bass note, we stretch the carrier waves out. We decrease its frequency.
So the information isn't in how loud the signal is anymore. It's hidden in the rhythm of the wave.
Exactly. And here is why that is so brilliant. When that thunderstorm hits, it still creates a big spike in amplitude. The radio wave still gets taller for a split second.
But the FM receiver doesn't care about height.
It's designed to ignore it completely. The FM receiver has a circuit called a limiter, which just chops off the top of any wave that's too tall. Its only job is to measure the spacing, the frequency between the waves.
So the lightning strikes, the wave jumps up, the limiter cuts it off, and the receiver just says, I don't care, the spacing didn't change.
And the static almost completely disappears. You get that clean, crisp sound quality FM is known for.
That is such a satisfying engineering solution. It's like you can't stop the storm, so you just switch the variable to something the storm is less likely to mess with.
That's the entire history of communication technology in a nutshell. Finding a cleaner, quieter place to hide the signal.
And eventually that leads us away from analog entirely and into digital, right? Which is the ultimate hiding spot.
It's the ultimate hiding spot because it's the simplest possible system. It's not about a little taller or a little shorter. It's just ones and arrows.
On or off.
On or off, or in more advanced systems, maybe switching the phase of the wave. But the point is, it's a discrete state. It's much, much harder for random noise to make an on signal look like an off signal than it is to make a slightly loud signal look a little bit louder. The margin for error is huge.
So, okay, let's recap. We've transduced the thought into electricity. We've modulated that electricity onto a carrier wave. Let's say it's a light wave in a fiber optic cable for this example, going digital.
Good example.
Now we have stage 3.
Propagation.
The journey.
And this is where the physics just gets mind-bending.
Yeah.
Because we're not talking about the speed of sound anymore. Sound is slow. It's about 340 meters per second in air. You can see a batter hit a baseball from the bleachers way before you hear the crack of the bat.
But electromagnetic waves, radio, microwaves, light.
They all travel at the same speed in a vacuum. And it's the speed limit of the universe, approximately 300,000 kilometers per second.
I always struggle to actually visualize that number. It just sounds impossibly big.
Okay, try this. In the time it takes you to snap your fingers, just one snap,
Yeah.
a beam of light could travel around the entire circumference of the Earth 7.5 times.
7 times. In a finger snap.
It makes distance on Earth basically irrelevant. For the purpose of almost all human interaction, it's instantaneous. But, and this is the real deep dive nuance here, it isn't actually instantaneous. It still takes time.
Which is why when we look at the stars, we're seeing them as they were millions of years ago. We're looking into the past.
Exactly. The light from Alpha Centauri, our nearest star system, takes over 4 years to get here. But even when you look at me across this table, you're not seeing me as I am now.
You're seeing me as you were a fraction of a nanosecond ago.
Right. You never, ever perceive the now. You are always living in the immediate past, lagging just behind reality, waiting for the wave to arrive.
Yeah, that's mildly unsettling. We're living in a permanent state of delay.
We are. And that delay is the time it takes for propagation. The wave has to swim through its medium, whether that's the vacuum of space or a glass fiber, or the air in this room.
Okay, so the wave finally arrives. It hits the receiver, my eye, my ear, my phone's antenna, and now we have to do the whole dance in reverse. Stage 4.
Stage 4, reception and decoding, or demargulation. You have to strip away the carrier wave. You thank the mule for its service, throw it away, and keep the baggage it was carrying.
So the antenna on my phone captures the modulated radio wave.
Your phone's circuits reverse the process. They extract that original electrical signal, the mimic of the voice, and then another transducer, the tiny speaker in your phone, converts that electricity back into mechanical vibrations.
And I hear the sound.
And you hear the sound.
And this whole 4-stage process happens, what, billions of times a second inside a modern computer?
Constantly. It's happening right now for everyone listening. Their brains are decoding the mechanical waves coming from their speakers, which were created by electrical signals, which were decoded from digital files that were transmitted over waves.
Yeah.
It's just an endless chain of energy conversion.
It's absolutely incredible. But we've been talking about this in terms of radios and phones and satellites, human inventions. But the notes make a really strong point here. We didn't invent any of this stuff.
Not a bit of it.
We just mimicked it. We reverse engineered it because we are walking, talking biological receivers. We have our own built-in antennas.
Do. And this is where we get into what the notes call the hierarchy of senses.
So we have the 5 classics, right? Sight, hearing, taste, touch, smell. But the argument here is that for the specific task of communication, 2 of these are doing pretty much all the heavy lifting.
That's right. If you define communication as the transfer of complex information across a distance, 3 of your senses are basically useless.
I mean, I guess it can't smell what you're thinking from across the room.
Exactly. Taste, touch, and smell are what we call proximity senses. You have to be in direct physical contact with the chemical or the object to get any information.
There's no propagation.
There's no propagation. If a tiger is a mile away, your sense of touch is useless. Your sense of taste is useless. Your sense of smell might work if the wind is just right, but it's slow and unreliable.
But if I can see the tiger or hear the tiger,
then you have high-quality information at a distance, and you can react. That is an enormous evolutionary superpower. So evolution doubled down hard on the 2 senses that can detect traveling waves, sight and hearing.
let's talk about sight first. The notes refer to it as the heavy lifter.
It's the bandwidth king. It's not even close. Some neurologists estimate that the human visual system processes something like 80% of all the sensory information we receive.
80%. That seems incredibly high. What about everything else we feel and hear?
Think about the sheer data density. If you just glance at a room in a fraction of a second, your brain processes the location of every chair, the color of the walls, the texture of the carpet, the intensity of the light, the subtle expression on someone's face. That is millions and millions of bits of data instantly.
And mechanically, how are our eyes actually catching that data? What's the transducer?
The transducer is the retina. We're detecting electromagnetic waves, but only a tiny, tiny sliver of the full spectrum. We call it the visible spectrum light, with a wavelength between about 400 and 700 nanometers.
Why that specific sliver? Why can't we see radio waves or X-rays?
That's a great question. And the answer is mostly the sun. Our star puts out the most energy, its peak output, in exactly that range of wavelengths.
So our eyes just evolved to be sensitive to where the illumination was strongest.
Exactly. We built our antennas to match the strongest broadcast station. And in our retina, we have millions of photoreceptors, rods and cones, that act just like that microphone diaphragm we talked about. A photon of light hits one, and it triggers a chemical reaction that creates a tiny neural spark.
And the key thing about vision, as the notes point out, is that it's fundamentally spatial, right? It's about where things are.
Yes, because light travels in overwhelmingly straight lines, your brain can do simple trigonometry. If a photon hits the left side of your retina, your brain knows with certainty that the object it came from is on your right. It uses this to build a 3D map of the world. Vision tells you where things are.
Okay, so that's vision, the high bandwidth spatial sense. But then we have hearing. And looking at the physics, sound is, well, it's kind of a mess compared to light.
It is. It's sloppy. It's incredibly slow. It doesn't travel in straight lines. It bounces around corners. It's very low resolution. You can't hear a photograph.
So if it's so inferior, why is it so important? The notes call it the foundation of language.
Because it does something vision can't. While vision is about space, hearing is all about time.
Elaborate on that. What does that mean? It's about time.
Speech is a sequence. It only makes sense as it unfolds over time, one word after another. Music is all about rhythm and tempo and pitch changes. Our ears and the auditory cortex in our brain are incredibly exquisitely tuned to detect tiny, tiny changes in timing and frequency.
And that's where the emotion comes from, isn't it? I can read a text message that just says, I'm fine, and I have no idea what it actually means.
Right, it's ambiguous.
But if I hear you say, I'm fine, with a cracked, wavering voice, I know everything. The data is in the delivery.
Exactly. The carrier wave of the voice, the tone, the volume, the tremor, the cadence, that carries the rich emotional data. That's why spoken language is the oldest and most universal form of communication. It connects us emotionally in a way a silent image often can't.
I love this idea that they're complementary. They're not just redundant backups for each other. They do different jobs.
They're a team, a perfect partnership. Vision builds the stage and shows you the actors. Hearing provides the script and the soundtrack.
There was a real aha moment for me in the reading in this section about what happens when you lose one of them.
The neuroplasticity part.
Yeah. It's not just that, say, a blind person pays more attention to sound. It's more profound than that.
Oh, it's much cooler than that. The brain is fundamentally hungry for data to build its model of the world. If the visual cortex, this huge part of the brain, suddenly stops getting input from the eyes, it doesn't just shut down and go dark.
It gets repurposed.
It starts getting colonized by the other senses. The auditory system starts feeding its signals over to the visual processing power. The brain starts trying to use that massive spatial mapping hardware to build a spatial map out of sound.
Like echolocation in bats or dolphins?
Exactly like echolocation. Some blind individuals can learn to make clicks and interpret the returning echoes to see the shape of a room. They're literally seeing with sound. It proves that the brain ultimately doesn't care where the wave comes from. It just wants the data to build a coherent model of reality.
That's incredible. So we've established that we are biological wave receivers built to interpret light and sound. But now I want to pivot to the rules of the road, because these waves, specifically light waves, they don't just fly around randomly. They follow very strict, predictable laws.
This is where we enter the formal realm of optics.
Optics, it sounds very clinical, very sterile.
Well, it comes from the Greek optikos, which just means of or foresight.
Yeah.
It's the branch of physics that deals with the behavior, properties, and, crucially, the manipulation of light.
The study guide breaks this down into two main branches, and I think this distinction is really helpful because I always get confused about when we're supposed to treat light as a particle-like ray and when we have to treat it as a proper wave.
Right. And it all comes down to a single concept.
Mm-hmm.
Scale. The scale of the objects the light is interacting with, compared to the wavelength of the light itself. So if you were looking at something incredibly tiny like light passing through a microscopic slit, or the iridescent colors on a soap bubble, you have to use physical optics, or wave optics.
Because the slit is so small, it's almost the same size as the wave itself.
Exactly. At that scale, the wave-like properties, diffraction, interference, they dominate. But if you're looking at a toaster or a face or a mountain,
The object is huge compared to the light wave. A light wave is a few hundred nanometers. A mountain is kilometers.
right, in that case, the wiggling, wavy nature of light is so insignificant that we can completely ignore it. We can just pretend light travels in perfect straight lines. We call those lines rays. That's geometric optics, and that's what we use to understand mirrors and lenses.
Which brings us to the first and most fundamental law of geometric optics, the law of reflection.
The oldest law in the book. Euclid was playing around with this, with mirrors and angles, back in 300 BCE.
And on the surface, it seems so simple. The notes state it as angle in equals angle out.
The tie, angle of incidence equals angle of reflection. It's beautifully elegant, but, and there's always a but in physics, people mess this up constantly
Why?
because they measure from the wrong place.
Okay, let's visualize this for the listener. I have a flat mirror lying on the floor. I shine a laser pointer down at it. The beam comes in, it hits the glass, and it bounces off.
Okay.
Naturally, my first instinct is to measure the angle between the laser beam and the surface of the floor.
Stop right there. That is the classic mistake that trips up every physics student.
But why? The floor is right there. It's the most obvious thing to measure from.
Because the surface is unreliable. What if it's a curved mirror, like on your car? The angle of the surface is constantly changing. What if it's a bumpy, uneven surface? The surface is a messy, inconsistent reference point. Physics demands a constant, reliable reference, so we have to invent one.
And this is the normal.
This is the normal. It sounds like a horror movie villain. Beware the normal.
Laughs, don't look at the normal.
It's actually very boring, I promise. It is an imaginary dotted line. You draw it sticking straight up, perfectly perpendicular to the surface of the mirror, at the exact spot where the light ray hits. 90 degrees to the surface.
So it's like a tiny flagpole sticking straight out of the mirror at the point of impact.
Exactly. It's a local, consistent reference point. And the ironclad rule is, you always measure the angle between the light ray and the flagpole, the normal. You never, ever measure from the floor.
That feels like an arbitrary choice physicists made just to make homework problems harder.
It really feels that way at first. But I promise, it saves you when things get complicated. If you have a spherical mirror, like in a funhouse, the surface is curving away constantly. But at any single point where a ray hits, you can always draw one unique, normal line sticking straight out. It gives you a consistent way to do the math no matter how weird the mirror is.
Okay, I think I get it. So the angle of incidence is the angle between the incoming ray and the normal. And the angle of reflection is the angle between the outgoing ray and the normal. And those two are always equal.
Always. Light is obsessed with symmetry.
So here's a question that stumped me for a little while when I was reading. If the law of reflection is true for all surfaces, why isn't everything a mirror?
Ah, yes. The classic specular versus diffuse reflection question.
Right, my wall reflects light. If it didn't, it would be perfectly black. If I shine a flashlight on the wall, the light bounces back and I can see the spot, but I can't see my face in the wall. Why not?
It all comes down to organization at a microscopic level. A mirror is smooth. And when I say smooth, I mean unbelievably atomically smooth. That's what we call a specular surface.
So if a billion parallel light rays from my face come flying in.
They hit that perfectly flat surface, and because the normal is pointing in the exact same direction for every single one of them, they all bounce off in the exact same parallel direction. They stay in formation. The image is preserved.
It's like a disciplined marching band turning a corner in perfect step.
That's a perfect analogy. Now, what about the wall?
The wall.
The wall feels smooth to your hand, but to a tiny light wave, which is only a few hundred nanometers long, that wall is a mountain range. It's jagged, it's rough, it's a diffuse surface,
So the marching band hits the mountain range.
and it's total chaos. One photon, one band member, hits a tiny peak that's angled to the left and bounces off left. The very next photon, a millimeter over, hits a tiny valley that's angled to the right and bounces off right.
But the law of reflection still applies to each one.
To every single photon individually. Angle in equals angle out relative to the normal of the tiny microscopic bump it happened to hit. But because the bumps are facing in millions of random directions, the light scatters everywhere.
The information gets scrambled, the pattern is lost.
Exactly. The energy returns. That's why the wall looks bright. But the coherent pattern that forms an image is completely destroyed.
I love that. The fundamental law never ever breaks. The geometry just gets too complicated for our eyes to reassemble the picture.
Physics never takes a day off. It just gets messier.
Speaking of geometry, the study guide has a whole section on ray diagrams. Now, describing a diagram on an audio show is always a challenge, but I think we can do it. This is basically about predicting the future, right? Predicting where the light is going to go.
It's about tracing the path. It's the bread and butter of optics. So everyone listening, just visualize a simple whiteboard in your head.
Okay, step one. We draw the mirror, just a straight vertical line, and we can put little hash marks on the right side to show that's the back of the mirror.
Good. Step 2. We draw the normal. Remember, that's a dotted horizontal line sticking out of the middle of the mirror at a 90-degree angle.
Step 3. Fire the laser. We draw an arrow, a ray, coming in from the top left, and it hits the mirror at the exact spot where the normal meets it. That's the point of incidence.
Now, you just look at the angle. Let's say it's coming in at a nice, clean 45 degrees relative to that dotted normal line.
So using the law,
The reflected ray must leave at 45 degrees on the other side of the normal. It has to bounce out towards the bottom left. The whole thing forms a perfect sideways V shape.
it's the bank shot in a game of pool.
It's exactly the bank shot in pool. Billiards is just applied optics with slightly heavier balls. If you hit the bumper at a 45-degree angle, the ball leaves at 45 degrees.
So what if I do scenario A from the notes? What if I shoot the laser straight at the mirror, right along the normal line, so it's perpendicular?
Well, what's the angle between the incoming ray and the normal in that case?
0. They're the same line.
The angle of incidence is 0, so the angle of reflection must be
0.
0. The light bounces straight back along the path it came from. It goes right back into the laser pointer.
And what if I do the opposite? What if I skim it along the surface at a really wide angle?
That's grazing incidence. A large angle, say 85 degrees to the normal. It hits, and it just skips off at 85 degrees, staying very low to the surface. It's exactly like skipping a stone on a lake.
Okay, we have the basic mechanics. Now, I want to get to the part of this that genuinely, honestly blew my mind when I was reading through the material. The concept of the virtual image.
This is the real mind bender. This is where physics meets psychology.
When I look in a mirror, I see myself. We all know this. But I don't see myself on the surface of the glass. I see myself behind the glass. It looks for all the world like there is a copy of me, another person, standing inside the wall.
And if you take a step backward from the mirror, the copy takes a step backward, deeper into the wall.
Why? I know there is no space behind the mirror. My logical brain knows it's a solid wall. Why does my visual system insist on putting the image there?
It's because your brain is stubborn. And, frankly, a little bit presumptive. Your brain has evolved over millions of years operating on one golden, unbreakable rule.
Which is?
Light always travels in straight lines.
But mirrors bend light. That's what they do.
Your brain doesn't know that. Or rather, it doesn't care. It doesn't factor the bounce into its calculations. Here's exactly what happens, step by step. Light from the lamp over your head bounces off your face. These rays travel to the mirror, they hit the mirror, they obey the law of reflection, and they bounce off and travel into your eye.
Got it. The physical path.
Right. Now, your eye catches one of these reflected rays, and your brain's interpretation software kicks in. It says, okay, this ray of light came into my eye from this direction. Therefore, the object it came from must be in a straight line back along that path.
It completely ignores the bounce at the mirror.
It ignores the bounce. It has no mechanism for processing a bounce. It extends that line of sight straight backward right through the surface of the mirror into the imaginary space inside the wall.
And it does this for every ray of light.
For every single ray.
Yeah.
One from your forehead, one from your chin. And because the geometry of a flat mirror is so perfect, all of those imaginary lines that your brain is drawing backward converge at a single coherent point behind the mirror. And your brain says, aha, that's where the face is.
So I'm hallucinating. Is that what's happening?
In a strictly physical sense, yes. You are perceiving an object in a location where no object exists. We call it a virtual image. Precisely because the light rays don't actually meet there. They only appear to diverge from that point.
What does that mean, don't actually meet there?
It means if you took a piece of paper, like a movie screen, and put it behind the mirror where your image appears to be, nothing would show up. The screen would be blank. The light isn't really there.
But the image looks so real. It feels real.
It looks perfectly real because the geometry is perfectly consistent. The virtual image created by a plane mirror has a few key characteristics. It's always upright. It's always the same size as the actual object. And this is the key. It is located at the exact same distance behind the mirror as the object is in front of it.
So if I am standing 1 meter away from the mirror, my brain thinks I am looking at a twin who's standing 2 meters away from me. 1 meter from me to the mirror, and then another meter inside the wall to the twin.
Precisely. You are looking at a geometrically perfect ghost, created by a simple physical law, and your brain's stubborn refusal to believe that light can change direction.
It really connects all the way back to the start of our conversation. We talked about connection. In this case, the connection I have with my own image is, in a way, an illusion. I'm connecting with a version of reality that doesn't physically exist, all constructed by the rules of my biological hardware.
It's the architecture of communication all over again. The signal is your face. It gets modulated by the reflection. It propagates to your eye, and it gets decoded by your brain. But the decoding process has this built-in glitch, this hardwired assumption of straight lines that creates a virtual world.
It makes you wonder how much of what we perceive every day is real and how much is just our brain decoding signals in the only way it knows how, with all its shortcuts and assumptions.
That is the ultimate question of optics, and maybe all of neuroscience. We don't see the world. We see the light that bounces off the world, and that light is then interpreted by a wet biological computer that evolved to take shortcuts to survive.
A wet biological computer. I love that. It's so accurate.
It's what we are. Flawed, brilliant decoders.
So let's try to wrap this up. We've covered a huge amount of ground today, from the macro to the micro.
We really have. We started with this abstract idea that information needs a physical vehicle, a wave to travel across any distance.
We looked at that 4-stage architecture. Transduction, turning ideas into signals, modulation, putting signals on a carrier, propagation, the journey, and reception, decoding it at the other end.
Now, we talked about our own biological receivers, sight and hearing, and how they evolve specifically to catch those waves that travel well over a distance, giving us information about space and time.
We defined optics and made that crucial distinction between the ray view, which is great for mirrors and lenses, and the wave view, which you need for really tiny stuff.
And we broke down the simplest, most powerful rule in the book, the law of reflection, angle in equals angle out, and how that simple rule, combined with the concept of the normal, explains everything from a shiny mirror to a dull matte wall.
And finally, we saw how that very same law tricks our brains into seeing these ghostly virtual images that seem to live behind the glass.
It's a lot to take in, but it really does change how you look at a simple thing, like a bathroom mirror or a radio dial. You start to see the underlying machinery.
It's all just physics playing out in real time everywhere, the machinery of reality.
That's it, exactly.
Before we go, I want to leave our listeners with one final thought, something that really popped into my head while we were discussing the normal.
Okay, what's that?
We spent a lot of time emphasizing that the normal, that dotted perpendicular line, doesn't physically exist. It's imaginary. It's a mathematical tool we draw on a diagram to make the calculations work.
Right, it's a construct.
And yet the physical world, the photon itself, obeys the measurements made against that imaginary line perfectly. The photon has no idea we drew that line, but it acts as if that line is the most important thing in the universe. Its behavior is governed by its relationship to our invention.
That is a profound observation. We impose a mathematical framework onto reality, and reality seems to fit into it perfectly.
It just makes me wonder, what else in our perception of the world is a normal? What other imaginary constructs do we use to make sense of reality that aren't actually there, but which seem to govern how we interact with the world?
You mean like the concept of time, the idea of a linear past, present, and future. Is that real, or is it just a normal line we draw to make sense of change?
Is time a normal? Is money a normal? Is the concept of a nation with its imaginary borderlines? These are all lines we draw to organize the chaos. They don't physically exist, but if we all stop believing in them, the picture completely falls apart.
We create the measuring stick, and then the world seems to align itself with our measurements. It's a very deep philosophical rabbit hole to fall down.
It is. So that's something for all of you to mull over the next time you catch your own reflection in a shop window. Remember, you're looking at a virtual image created by a physical law, measured against an imaginary line.
And yet, it all looks perfectly real.
Thanks for listening to this deep dive. Hopefully, the signal came through clear for you. We'll see you next time.
Keep connecting.
Welcome back to the deep dive. I want to start today by asking you to do something that feels, well, incredibly simple.
Okay.
But it's actually physically impossible without a massive amount of hidden machinery going on behind the scenes.
I'm intrigued.
I just want you to look around the room you're in. That's it. Just look at a wall or your hand or the road ahead if you're driving.
It feels instant, doesn't it? You open your eyes and the world is just there.
Exactly. It feels passive. It feels like seeing is just about letting the world in. But the more I looked into the research for today's deep dive, the more I realized that is completely fundamentally wrong. Seeing isn't passive.
No, it's not.
It's a construction project.
That is the perfect way to frame it. We are not cameras just recording reality. We are actively interpreting a very, very specific slice of physics.
So today we are diving back into optics. This is optics part 2, but we're not just talking about what light is.
Right. We did that last time.
This time, it's about how we manipulate it. We are talking about warping reality with mirrors, bending it with lenses, and then finally capturing it with sensors.
And this is where it gets really weird.
Honestly, some of this stuff makes me question if I can even trust my own eyes.
You definitely shouldn't.
Great. That's comforting.
Well, not entirely, but they do lie to you.
So to kick this off, I want to talk about the morning routine, because this is where most of us encounter the strangeness of optics without even realizing it.
Okay.
You wake up, you stumble into the bathroom, you look in the main mirror above the sink.
Your standard flat mirror.
And you look like you. You know, normal size, right way up, maybe a bit tired.
That's a plane mirror.
Yeah.
It's the boring baseline of optics. It does exactly what you expect it to.
But then, let's say you're in a fancy hotel, or you have one of those special makeup mirrors. You know, the ones on the extending arm.
Oh, yeah. The ones that reveal flaws you didn't even know you had. The high-definition horror mirrors.
Yeah, exactly those. You flip it to the magnified side, you lean in to shave or put on eyeliner, and suddenly, bam, you're massive.
Your eye is the size of a dinner plate.
It is. But here's the part that always, always freaks me out. If you back away from that same mirror, just, you know, walk 3 or 4 feet back.
Ah, yes. The fun part.
You don't just get smaller, you flip upside down.
It's a complete inversion of your reality.
Why? Why does one piece of glass just show me my face, while this other one flips me upside down if I stand too far away, but zooms way in if I get close? That is the mystery we are unpacking today.
It really all comes down to 2 things: geometry and information. That's it.
Geometry and information.
We're going to go on a journey through the shape of mirrors, specifically curved ones. Then we're going to look at what we call the big 3 properties of images.
Big 3. Okay, I like that. It sounds important.
It's fundamental. It's the framework physicists use to describe exactly what you're seeing. Then we're going to switch from bouncing light to bending light. We'll talk about lenses, refraction, and the actual math behind your glasses prescription.
I am very excited about that part because I have been wearing glasses since the 4th grade, and I have never, ever understood what those numbers actually mean.
We will absolutely decode it for you. And then finally, we end with the unsung hero of all of this.
Which is?
The sensor.
Yeah.
Because you can bend light and bounce light all you want, but if nothing is there at the end of the line to catch it,
Does it even matter?
exactly. Does the image even exist? It's
Mm.
the, if a tree falls in the forest, question of optics.
It is. Okay, let's do this. Let's unpack it. Let's start with the geometry of reflection. We're used to flat mirrors.
Right.
Boring. But things get wild when you start bending the glass. So why is a curved mirror so fundamentally different?
Okay, to understand a curved mirror, you have to stop thinking about the mirror itself for just a second.
Okay.
I want you to imagine a sphere, a giant hollow ball made of glass. Let's say it's 10 feet wide, just floating in the middle of a room.
Got it. A giant glass beach ball in my head.
Perfect. Now, imagine you take a glass cutter and you just slice a circular piece off the side, like you're cutting a cap off it.
Like a saucer.
Exactly, like a saucer. That slice, that is your curved mirror.
So every curved mirror is it's just a segment of a much bigger sphere.
That's it. And because it came from a sphere, it inherits a kind of ghost geometry. Even though you threw away the rest of the ball, the mirror still behaves according to the center of that original sphere.
So there are invisible points in space that are dictating how this thing works.
Few of them. And they are critical. The first is called the center of curvature, which we just call C.
C for center.
Yep. And that is literally the center point of that original 10-foot sphere we imagined. So if you're holding the mirror, C is a point just floating in the air, maybe 5 feet in front of you.
Okay, so C is the anchor point. It's the ghost of the ball it came from.
Precisely. And the second point is the principal focus, or F.
F for focus.
This is the magic spot. It sits exactly halfway between the surface of the mirror and that center point C.
So if the center of our sphere is 5 feet away from the mirror, then the focus is at 2.5 feet.
You got it. And that distance from the mirror to F has a name. It's called the focal length.
Focal length. I've heard that with cameras.
It's the same concept. In optics, focal length is everything. It tells you how powerful the mirror is. A really short focal length means the mirror is very curved, very powerful.
In a long focal length.
Means it's almost flat. Not very powerful at all.
Okay, so we have the anatomy down. A slice of a sphere, an invisible center point C, and an invisible focus F. Now, in the notes, we've got two main types of curved mirrors. I like the names you used. The cave and the spoon.
It's a good way to remember it. Let's start with the concave mirror.
Concave mirror. I always remember this because it caves in.
Like a bowl or a cave, exactly. It curves inward away from you. And because of that specific shape, it is a converging mirror. This is crucial. When parallel light, rays like sunlight from very far away, hit this bowl shape.
They don't just bounce off randomly.
No, the curve forces them all to bounce inward. They all get funneled, and they crash together at one single specific spot.
And let me guess. They crash together at F, the focal point.
That is exactly why it's called the focus, is where all the light concentrates. It's why you can take a concave mirror and use it to start a fire.
Right, you hold a piece of paper right at that F spot in the sun, and all the sun's energy hitting the whole mirror gets focused onto one tiny point.
And it'll catch fire. That's how a solar cooker works. It's just
Yeah.
a big concave mirror.
That makes so much sense. Now, in the reading, there was this section about ray construction rules. It felt a little bit like a logic puzzle. There are 3 rules that tell you exactly where an image will appear.
Right.
Do we need to memorize these to understand this?
You don't need to memorize them, but understanding them kind of unlocks the magic. It shows you that light isn't random. It follows a very predictable track.
Okay, so what's rule 1?
Rule 1. If a ray of light comes in parallel to the center line of the mirror, it will always reflect through the focal point F.
Okay, parallel in, through focus out. Simple enough.
Rule 2 is just the reverse. If a ray goes through F first on its way to the mirror.
It reflects out parallel.
Exactly, it's perfect symmetry.
Got it. And the third one?
The third rule is the boomerang. If a ray of light happens to pass through the center of curvature C on its way to the mirror.
The original center of the sphere.
Yes, it hits the mirror dead on at a perfect 90-degree angle, and it just bounces right back along the exact same path it came from.
So using these 3 rules, we can basically play connect the dots and predict exactly what we'll see.
We can. And this is where I want to try something. I want to take you and everyone listening on a mental walk.
Okay,
Because you really have to visualize this to feel how trippy it is.
let's do it.
Imagine we are in a long, dark hallway. At the far, far end, There is a massive concave mirror. It's floor to ceiling. It's huge.
Okay, giant mirror at the end of a hall.
And let's give it some numbers. Let's say the center of curvature C is 20 feet in front of the mirror, which means the focal point F is at 10 feet.
Okay. C at 20 feet, F at 10 feet. I'm standing at the start of the hall looking toward it.
So let's start way back.
Yeah.
Let's say you are 50 feet away. You are well beyond C. You look into the mirror. What do you see?
Well, based on the telescope analogy from the notes, I'm guessing I see myself, but I'm tiny.
You are tiny, yes.
Yeah.
But there's more. The light rays bouncing off your face travel down the hall, hit the mirror, and because it's a converging mirror, they converge. They actually cross over each other in space in front of the mirror before they get to your eyes.
They cross over.
They do. And because they cross, the image flips. What was on top is now on the bottom.
So I see a tiny upside-down version of myself just kind of hanging in the air.
Yes. A perfect miniature inverted U. This is scenario A. The image is, in technical terms, real, inverted, and diminished.
Okay, and this is how a telescope works.
This is exactly how a reflecting telescope works.
Mm-hmm.
It looks at a star, which is huge, but it's so far away it's effectively at infinity. And it creates a tiny, real, inverted dot of light right at the focus. Then you use an eyepiece to magnify that dot.
Wow. Okay, so I'm a tiny upside-down person. Now I keep walking down the hall. I pass the 20-foot mark. I am now between the center C and the focus F. I'm, say, 15 feet away from the mirror.
You are in scenario B. You are getting closer to that magical focal point. The geometry shifts, the rays still cross, so you are absolutely still upside down.
Still inverted.
But now the angles are steeper. The image gets pushed further out away from the mirror, and it grows. It gets bigger.
So I'm still upside down, but now I'm magnified.
You are. This is real, inverted, and magnified.
Is there a real-world example of this one?
This is a cinema projector. Think about it. The film strip or the digital chip is the object. It's small. You place it just outside the focus of the lens system, between F and C, and what does it do? It throws a massive, real, inverted image onto the screen on the other side of the room.
Wait a second, but if the projector creates an inverted image, why aren't all the movies we watch upside down?
Because the projectionist loads the film reel into the projector upside down.
No way.
Yes, the optics flip it so it ends up right side up on the screen. It's a beautifully simple, low-tech solution.
That is deceptively simple. I absolutely love that. Okay, back to the hallway. My upside-down self is getting bigger and bigger as I walk forward.
It is.
Now, I'm getting a little nervous. I'm stepping right onto the 10-foot mark. I am standing exactly on the focal point F.
This is the weird spot. This is scenario C. You could call it the singularity.
What happens?
Remember our rules. Rule 1 said parallel rays go through the focus, and Rule 2 said rays from the focus go out parallel.
Right.
Well, you are now the source of light at the focus, so all the rays from your face hit the mirror, and they all converge. Perfectly parallel.
So they never cross.
They never cross. And they never spread out. They just shoot out in a perfectly straight, collimated beam forever to infinity.
So? I don't see an image of myself.
No image. You just see a blur of light. The image has effectively disappeared, or you could say it's at infinity.
That feels useless.
For seeing an image, yes. But this is incredibly useful. If you replace you with a high-powered light bulb, what have you just created?
A beam of light. Like a lighthouse.
A lighthouse.
Mm.
Or a car headlight. Or a tactical flashlight. That powerful focused beam that cuts through the night. That is only possible because the bulb is sitting exactly at the principal focus of a concave reflector.
So at this one specific spot, the mirror isn't for seeing an image at all. It's about directing energy.
Exactly. It collimates the beam, makes it straight.
Incredible. Okay, one last step. I take one more step forward. I step inside the 10-foot mark. I am now, say, 5 feet from the mirror. I'm in the danger zone, close to the glass.
You are. This is the shaving mirror zone, scenario D.
So what happens now?
You have crossed the threshold. You are now inside the focal length. The light rays from your face are hitting the mirror at such a wide, steep angle that even the powerful curve of the mirror can't force them to cross.
They can't converge.
No. They bounce off and they're still spreading out. They diverge.
So if they're spreading out, they never meet, which means no real image.
No real image, but your brain. Your brain is a pattern-seeking machine. It has evolved over millions of years with one core assumption. Light travels in straight lines.
Okay.
So it sees these spreading rays coming at it, and it says, hold on, these rays are diverging. They must be coming from a single point behind the mirror. And it traces them back.
So it hallucinates an origin point.
It constructs a virtual image behind the mirror. And because the rays never physically crossed, the image is right side up.
Upright.
And because of the geometry of how your brain traces those rays back, it appears massive.
Virtual, upright, magnified.
That is the trifecta. That is why when you lean into the shaving mirror, suddenly you were huge and the right way up. But the second you back away past that 10-foot focal point,
I slip upside down again.
you transition instantly back to the real inverted image.
It is absolutely wild that just taking one step can completely change the fundamental physics of what you see. From a tiny upside-down ghost to a massive right-side-up face.
Concave mirrors are the divas of optics. They are high maintenance and highly variable.
So if the concave mirror is the dramatic diva, the convex mirror must be
Right.
the accountant.
The reliable, boring, predictable accountant.
Yes.
That's a great way to put it.
So a convex mirror curves outward, like the back of a spoon.
Right. It bulges towards you. And that bulge has one and only one job.
And what's that?
To scatter light. It is a diverging mirror. No matter where the light comes from, a convex mirror always pushes the rays apart.
So they never cross in front of the mirror.
They never physically cross, which means you can never, ever get a real image.
And if you can't get a real image, you can't get an inverted one.
You can't. The drama is gone.
So what is the rule for convex mirrors then?
It is the consistency rule. No matter where you stand, 1 inch away, 100 feet away, it doesn't matter. The image is always the same.
And what is it?
It is always virtual, upright, and diminished.
Always smaller.
Always smaller.
So why on earth would we want a mirror that makes everything look tiny? That seems like a design flaw.
It's all about the trade-off. Think about it. If everything in the reflection is smaller,
You can fit more stuff in.
you can fit more of the world into the reflection. It massively increases your field of view.
Ah, right. That's why we see them in the corners of convenience stores.
Exactly. The big, round security mirrors. If you're a shopkeeper, you don't need a magnified, high-resolution view of a single can of soup.
No, you need to see the whole aisle. You need situational awareness.
That's the perfect term for it. And of course, the most famous application of this.
Tar wing mirrors.
Objects in mirror are closer than they appear.
I feel like I've read that sentence 10,000 times in my life and never really thought about it.
That warning label is there purely because of the physics we're talking about. The mirror is convex to give you that wide view of the highway, which is great for safety. You can see the cars in your blind spot.
Right.
But because the image is diminished, it makes that huge truck look smaller. Your brain's hard wiring interprets small as far away.
So the mirror is basically lying to our built-in depth perception
It is.
in order to give us better peripheral vision.
It's a deal with the devil of optics.
Hmm.
We trade distance accuracy for angular coverage. And we slap a warning sticker on it so you don't merge directly into a semi-truck.
That is a trade-off I am more than willing to make.
I think we all are.
This brings us to a really key part of the framework you mentioned right at the start, the big three.
Yes.
We've been tossing these terms around, magnified, inverted, virtual, but let's formalize it. You said physicists always describe an image with these three tags.
Always. It's like the ID card for any image. If you're going to describe what a mirror or a lens does, you have to answer 3 questions.
Okay, what's question 1?
Question 1 is size. Is the image magnified, meaning it's larger than the actual object? Is it diminished, smaller than the object? Or is it the same size?
Okay, magnified, diminished, same size. Simple enough.
Question 2 is orientation. Is it upright, the right way up? Or is it inverted, upside down?
Also straightforward. We've seen both of those.
In question 3, this is the tricky one that trips people up. Is the image real or virtual?
Okay, let's drill down into this because I think this is where people can get a little lost. I certainly do sometimes. What is the actual physical difference?
The ultimate litmus test is a simple piece of paper.
A piece of paper. How does that work?
A real image is formed where light rays actually physically converge at a point in space. The photons are really there. There is energy concentrated at that spot.
So light is actually hitting that point.
Yes. So, because the energy is there, if you put a piece of paper or a screen at that exact spot, the image will appear on the paper. You can project it.
Like a movie theater.
A movie theater is the perfect example.
Yeah.
The projector throws light, the rays converge on the screen, and you see the movie. That is a real image.
Got it. And you mentioned a cheat code for this.
The cheat code is real images are, for single lenses or mirrors, almost always inverted.
Okay, so real equals projectable and usually upside down.
Exactly. Now, a virtual image is totally different. It's where light rays appear to be coming from, but they're not. There's no light there.
So the light is actually spreading out.
It's diverging.
Mm.
But our eyes and our brain trace those spreading rays backward in a straight line to a phantom point of origin.
So if I held a piece of paper behind my bathroom mirror where my reflection seems to be.
You just have a piece of paper behind a mirror. Nothing would be on it. There's no light there to project. The image is strictly in your head.
That is kind of disturbing. My reflection isn't really in the mirror at all.
It's an optical illusion that we've all just accepted as a normal part of reality.
And the cheat code for this one.
Virtual images are always upright.
Okay, that is a really handy memory rule. Virtual is upright, real is inverted.
It works for almost every standard case in basic optics. If you're looking at yourself in a mirror and you are the right way up, it's a virtual image. If you're looking at a projection on a wall, it's a real image.
I love shortcuts like that. So we've pretty much mastered bouncing light reflection.
We have.
But so much of our world isn't about bouncing. We look through things, we wear glasses, we use cameras, we have corneas in our eyes.
Right, and this is the transition from reflection to refraction.
Bouncing to bending.
Exactly.
So why does light bend when it goes through glass or water? I mean, I thought one of the fundamental rules was that light travels in straight lines.
It does, in a vacuum. In empty space, light is the undisputed speed limit of the universe. Nothing is faster.
Right.
But when it hits a denser material like air or water or glass, it basically hits traffic. It slows down.
It physically moves slower through the glass.
It does. And that change in speed is what causes the change in direction, the bending.
How does that work?
The classic analogy is a shopping cart
Okay.
or even a car. Imagine you're driving a car on smooth, fast pavement.
Okay.
And suddenly, your right side wheels drive onto a patch of thick, slow mud.
Okay, so the right wheels slow down instantly.
But the left wheels are still on the pavement, right? So they're still moving fast. So for a split second, the left side of the car is moving faster than the right side.
And the whole car would pivot, it would turn into the mud.
Exactly. That is refraction. When a wavefront of light enters a denser medium, it slows down and bends toward what we call the normal. That's just an imaginary line perpendicular to the surface.
And when it leaves the glass and goes back into the air.
It speeds up and it bends away from the normal.
And there's a law for this, right? It's not random.
It's very predictable. It's called Snell's law. It calculates the exact angle of the bend based on the optical density or the refractive index of the material.
So denser glass bends light more.
Much more. A diamond, for example, is incredibly dense optically. It slows light down to less than half its vacuum speed. It bends light so violently, which is why it sparkles so much.
Okay, so we can use this predictable bending to build lenses. And it looks like we have the same two characters here as we did with mirrors. A convex one and a concave one.
We do, but here's the plot twist.
Oh,
They swap roles.
the old switcheroo. Okay, how so?
Let's look at the convex lens. This is the classic lens shape. Thicker in the middle, thin on the edges, like a magnifying glass.
Got it.
Now, when parallel light hits a convex mirror, it scatters.
Yeah.
But when it hits a convex lens, the shape forces the light to bend inward toward the thickest part.
So it concentrates the light. It's a converging lens.
Exactly. Convex lens acts just like a concave mirror.
So it brings the light to a focus point.
It does. And because it converges light, it can create all those same dramatic scenarios we talked about in the hallway experiment.
The whole walking in sequence with a lens.
Yep. If the object is far away from the lens, beyond what we call 2f, which is just twice the focal length, you get a real inverted, diminished image.
A tiny upside-down projectable image. What uses that?
The human eye.
Wait, hold on. My eye has a convex lens.
It does. Your cornea and the lens behind it act as a strong convex lens system.
So does that mean the image that forms on my retina at the back of my eye, is it upside down?
It is. Right now, as you look at me, the lens in your eye is projecting a tiny, real, inverted image of me onto the back of your eyeball.
So why isn't the world upside down for me right now?
Because your brain is an absolute software genius.
Yeah.
It takes that inverted, raw data from the optic nerve and it just flips it right side up in real time without you ever noticing.
That is unbelievable.
There have been amazing experiments where people wear special prism glasses that flick the world upside down before it even gets to their eyes.
Oh, I've heard about these.
For the first few days, they're stumbling around, they feel sick. But after about a week, their brain adapts and flips the image back. They start seeing the world normally again, even with the glasses on.
And then when they take them off?
The world looks upside down again until their brain recalibrates back to the original setting.
We are all just walking around with upside-down raw data that our internal software is constantly patching on the fly.
Constantly. Now back to the lens. If you bring the object closer, between f and 2f.
Let me guess. Real, inverted, magnified.
You got it. That's a slide projector or a traditional microscope objective.
And if we get really, really close, inside the focal length,
Just like the concave mirror, it becomes a magnifier. Virtual, upright, magnify. That's your standard magnifying glass.
okay, so the convex lens is the converger, just like the concave mirror. So I'm guessing the concave lens is the diverger.
That's it. A concave lens is thinner in the middle and thick on the edges. That shape forces light to spread out. It is a diverging lens.
And let me guess. It behaves just like the convex mirror. The boring accountant.
You got it. It's the reliable, consistent one. A concave lens always produces a virtual, upright, and diminished image.
So why would we want a lens that spreads light out and makes things look smaller? If the whole point of a lens is to focus, isn't spreading it out bad?
It's not bad if you're trying to fix a broken eye,
Ah, right, glasses.
specifically for correcting myopia, or what we all call short-sightedness.
Which is what I have. I can see things up close, but I can't see distance clearly.
So optically speaking, your eye is too strong.
Too strong? How can it be too strong if it can't see far away?
It's counterintuitive, I know,
Yeah.
but it means the lens in your eye bends light too much. It's too powerful. Or your eyeball is just a little bit too long.
Okay.
Either way, the light from a distant object converges too early. It creates that sharp, focused image somewhere in the middle of your eyeball jelly in front of the retina.
So by the time the light actually hits the retina at the back.
And rays have already crossed over and are spreading out again. It's a blur.
So how does the concave lens fix my too strong eye?
We put a concave, diverging lens, your glasses, in front of your eye. It takes the incoming parallel light and spreads it out just a tiny bit before it even hits your eye.
So it's like a head start. It pre-diverges the light.
Exactly. It counteracts the excessive strength of your eye's natural lens. It pushes that focal point back just a few millimeters so it lands perfectly, sharply, right on your retina.
That makes perfect sense. You're pre-spreading the light so that my overeager eye can focus it correctly.
That's a perfect description of it.
This leads us right into the math. And I know some listeners might cringe at the word math, but this is actually really practical.
It is.
When I go to the optician, they don't say, give him a concave lens to pre-spread the light. They give me a number, negative 3.5 or plus 2.0. What is that number?
That number is the power of the lens. And it's not just some random scale they made up. It is a specific mathematical value that is derived directly from the focal length.
We have a formula for this, I see.
You do. And it's one of the simplest and most elegant in physics. The formula is just P equals 1 divided by F.
Okay, P equals 1 over F.
Where P is the power, which we measure in a unit called dioptries, usually just capital D.
Dioptries. Okay, and F is the focal length.
Right. And this brings us to the inverse relationship. Why is it 1 over F?
Yeah, why is it upside down?
Well, think about what power means for a lens. A really powerful lens is one that bends light very, very sharply.
Right, it's strong.
So it grabs those rays and forces them to meet really quickly, very close to the lens.
So it has a short distance to the focus, a short focal length.
A short focal length, exactly. A weak lens, like an almost flat piece of glass, barely bends the light. So the rays take a long, long time to converge.
A long focal length.
So you see the relationship. High power equals a small number for F. Low power equals a big number for F. They're inverses.
That makes perfect intuitive sense. If I have a totally flat piece of glass, the parallel rays never meet, so the focal length is infinity.
Correct.
And 1 divided by infinity is, for all practical purposes, 0.
0 power. Flat glass has 0 dioptries. It works perfectly.
Now, you mentioned a trap with the units here.
No, this is the classic banana peel that trips up every single physics student on their exam. Every time.
Okay, what is it?
The formula, P equals 1F, only works if the focal length, F, is in meters.
Meters.
But in the real world, and especially in textbook problems, we almost always measure focal lengths in centimeters. You know, the 20-centimeter lens, a 50-centimeter lens.
Right. Those are more manageable numbers. So let's walk through an example. Let's say I have a lens with a focal length of 20 centimeters. I want to find its power.
Okay.
If I forget the rule and I just plug in 20.
You'd calculate 1 divided by 20, which is 0.05 dioptries.
And that's wrong.
That's incredibly wrong. 0.05D is basically a window pane. It has almost no power.
So I have to convert first.
You must.
Yeah.
Step 1 is always convert to meters. So 20 centimeters is...
0.2 meters.
Right. Now do the math. What is 1 divided by zero point 0.2?
That's 5.
5 dioptries. That is a very strong lens. The difference between 0.05D and 5D is massive. It's the difference between a window and a powerful magnifying glass.
So the moral of the story is always convert to meters first.
Always.
Okay, what about the plus and minus signs on my prescription? Mine says my NAT is 3.5. What does the negative actually mean?
The sign is just a code. It tells you the type of lens. This is what we call the sign convention.
Okay.
Converging lenses, the convex ones that bring light together, are considered to have a positive focal length, so they have positive power.
So a plus sign means a converging convex lens.
Right, whereas diverging lenses, the concave ones that spread light out, have a negative focal length and therefore negative power.
So if I'm a Magnus 3.5, that means I have a diverging concave lens.
Yes, which confirms what we already knew, that you were short-sighted or myopic. You need that negative lens to spread the light out to fix your too strong eye.
And if someone's prescription was, say, plus 2.0?
They would be long-sighted or hyperopic. Their eye is too weak and can't bend light enough, so we give them a positive convex lens to add some converging power.
So those cheap reading glasses you can buy at the drugstore that just say plus 1.5 or
Right,
plus
like-
2.0.
Those are just simple, off-the-shelf convex lenses. They add focusing power for people whose aging eye lenses have become less flexible and struggle to focus on close objects.
It's amazing that a single number can tell you the shape of the glass, the type of curve, the focal length, and what's wrong with your vision. It really is a secret code.
It is the language of optics, boiled down to one number.
Okay, so we've done it. We've generated this perfect image. We've used a mirror or a lens. We've calculated the dioptries. We've focused the light exactly where we want it to be.
The hard part is over.
But here's the kicker, and this is the final crucial part of our journey. If nothing is there to see it, it's just energy floating in space. It doesn't mean anything.
And this is where we leave the world of pure geometry and we enter the world of information theory. We need a sensor.
You define a sensor in the notes as a transducer. That sounds very sci-fi. What does that mean?
A transducer is just a fancy engineering word for any device that converts one form of energy into another.
A perverter.
That's all it is. But usually, it's converting some kind of physical energy into a signal, into information.
It's like translating a language.
That's a perfect analogy. Information is encoded out there in the world in the form of waves, light waves, sound waves, radio waves. But our brains, or the computers, they can't read waves directly.
They need a different format.
They need a signal. They speak the language of electricity.
So the sensor is the crucial bridge between the physical wave in the universe and the electrical data processing in our heads or in a chip.
It is the gatekeeper. It's the translator. The whole universal chain of information is source, encode, dash, transmit, dash, detect, dash, decode.
Yeah.
The sensor is the detect step.
Okay, let's look at the ultimate biological sensor, the eye. We talked about the lens focusing the image, but the retina at the back of the eye is the actual sensor, right?
The retina is the transducer.
Yeah.
It is a biological miracle, frankly. It is lined with millions and millions of tiny specialized cells called rods and cones.
Rods and cones. I remember those from biology class.
When a single photon of light, one particle of light, travels through your eye and hits one of these cells, it triggers a chemical reaction. A protein molecule literally changes its shape.
So it's a chemical trigger.
Yes. And that chemical change opens a channel in the cell membrane, which fires an electrical nerve impulse down the optic nerve to your brain.
So it converts light into an electrical signal?
Precisely. Light to electricity. The cones are the cells that handle color vision, but they're power hungry. They need bright light to work properly.
And the rods.
The rods are your black and white sensors, but they are incredibly, exquisitely sensitive. Some can detect a single photon. They are your night vision.
That's why colors always seem to fade away in the dark.
Exactly. Your color sensors, the cones, have gone offline. You switched over to your backup, high sensitivity black and white sensor array, the rods.
Now let's compare that to a digital camera, the thing we all carry around in our pocket every day.
A digital camera is doing the exact same job, but it's using silicon instead of protein.
The CMOS chip or the CCD sensor.
Right. A camera sensor is just a grid of millions of tiny little light-sensitive squares called photodiodes. Think of each pixel as a tiny bucket.
Okay.
When it rains light, the buckets fill up.
But they're not catching water, they're catching photons.
Yes. And when a photon hits the silicon of the photodiode, it has enough energy to knock an electron loose. That creates a tiny electrical charge.
So the more light, the more charge.
Exactly. At the end of the exposure, the camera's processor just goes around and counts the amount of charge in each bucket. It says, okay, this bucket is full, so this pixel is bright white. This bucket next to it is empty, so this pixel is black.
Again, it's just converting light into electricity.
It's the same fundamental mechanism, just executed with different hardware. Biological versus technological.
What I love about this concept of transduction is that it applies to everything, not just light. What about radio? How does an antenna work?
A radio antenna is a sensor for electromagnetic waves that are just much, much longer than light waves. The wave, which is an oscillating electric and magnetic field, hits the metal stick of the antenna.
Right.
Because it's an electric field, it pushes and pulls on the free electrons inside the metal. It literally shoves them back and forth.
It makes them move.
And what is a directed movement of electrons?
An electrical current.
It's an alternating current. The antenna directly converts the wave energy into electrical current. Then the radio circuitry amplifies and decodes that current back into sound.
Amazing. And the ear?
The ear is a mechanical sensor. Sound is a pressure wave in the air. That wave of pressure hits your eardrum and makes it vibrate.
Okay, so a physical movement.
That mechanical vibration is passed through 3 tiny bones, the hammer, anvil, and stirrup, which acts as an amplifier, into a spiral-shaped thing called the cochlea.
And the cochlea is lined with tiny hairs,
which wiggle in the fluid and their movement triggers.
You guessed it, electrical nerve signals that go to the brain.
It always ends up as a signal that the processor, whether it's wetware or software, can understand.
It's absolutely fascinating that no matter the input light, sound, heat, radio waves, the goal is always to translate it into that common language of electricity.
But there's a catch. And this is a huge, huge part of modern science and engineering. Sensors are not perfect.
The signal-to-noise ratio.
Right. The universe is noisy. And I don't just mean loud, like with sound. I mean energetically noisy. There's background radiation left over from the Big Bang. There's thermal jitter from heat. There's random interference from every power line and cell phone on the planet.
So a sensor doesn't just pick up the signal you want it to pick up. It picks up all that junk, too.
Imagine you're at a really loud cocktail party. You're trying to listen to your friend whispering something important to you.
Okay.
Your friend's whisper is the signal. The roar of the party is the noise.
If I can't hear them, I might cut my ear, make my sensor more sensitive and directional.
Right. But if you just turn up the volume on everything, like with a hearing aid, you amplify the crowd noise just as much as you amplify the whisper.
So you don't gain anything.
That is the fundamental challenge of all sensor engineering. The whole game is maximizing your sensitivity to the signal while minimizing your sensitivity to the noise.
Is that why they build those giant radio telescopes in the middle of deserts miles from anything?
That's exactly why. To get away from the electronic noise of city, radio traffic, Wi-Fi, everything. And it's why the highest-end astronomical cameras, like on the James Webb Telescope, are cooled with liquid nitrogen or helium.
To freeze them? Why?
Because heat itself is noise. Heat makes electrons in the sensor jiggle around randomly. That random jiggling creates a false signal. It looks like a faint glimmer of light that isn't really there.
So you cool the sensor way down to quiet that thermal noise?
You quiet the noise so you can hear the faint whisper of a galaxy billions of light years away.
That is beautiful. It's about creating an artificial silence so you can hear the universe.
That's a very poetic way of putting it. I like that.
Well, we have traveled the entire path of a light ray today. It started at a source, maybe a star or just a light bulb in a room.
Then it bounced off a curved mirror, maybe getting flipped upside down and magnified in the process.
Or it bent its way through a lens, slowing down and changing direction based on the precise density of the glass.
We even quantified that bend with a single number. Diopters decoding the secret language of optometrists.
And then finally, at the end of its journey, it slammed into a retina or a silicon chip.
Where it was converted from a wave of pure energy into a spark of pure information.
It really just drives home the point we started with, doesn't it? Seeing is such a constructed process.
It really is.
We think we just see the world as it is, but really we are interpreting a heavily processed signal that has been bounced and bent by physics before it ever reaches our consciousness.
That's a humbling thought, isn't it? Our entire view of reality is completely dependent on the quality of our biological sensors and the specific geometry of the lenses in our eyes.
And it raises a final and I think a slightly provocative question for you to think about.
What's that?
Well, every sensor has a limited range. Our eyes only see this tiny, tiny slice of the electromagnetic spectrum we call visible light.
Right. 400 to 700 nanometers. A sliver.
And our ears only hear from about 20 to 20,000 hertz. We are completely deaf and blind to UV light, X-rays, radio waves, gamma rays.
Without our technology, we are blind to 99.9% of the information flooding the universe.
So if seeing is just the act of detecting signals with sensors, imagine what images of reality are surrounding us right now, filling this room. What information is passing through your body that we simply don't have the biological or the technological sensors to detect yet?
What are we missing?
What are we missing simply because we haven't built the right transducer?
We are swimming in a sea of invisible information.
Something to think about while you stare at the ceiling tonight.
Indeed.
Well, on that note, I'm going to go look in my rear view mirror, my convex, diverging, field of view enhancing mirror, and just appreciate the fact that the car behind me is just a virtual image constructed by my brain.
Just remember, it is closer than it appears.
Thanks for listening to The Deep Dive. We'll see you next time. Welcome back to The Deep Dive. I want to start today with a specific feeling. I think everyone listening has had this moment. You're sitting in a coffee shop, or maybe you're just on a bus. You pull this little rectangle of glass and silicon out of your pocket. You tap the screen with your thumb and
instantly you're connected to the world.
exactly. 3 seconds later, you are watching a live video feed from a street corner in Tokyo. Or, you're listening to a voice from the literal other side of the planet.
It is, it's a feeling of wizardry, really.
It totally is. It feels like magic. It feels completely detached from the physical world. We use words like the cloud or the web, right? As if these things are just floating in some ethereal dimension. I mean, it really feels like this digital revolution is something that just appeared out of nowhere in the last 20 or 30 years.
Yeah, it creates a real sense of disconnection. We tend to think the digital world is somehow separate from the real physical world.
Right. But looking at this stack of research we have for today, these incredibly deep notes on the history of signaling, wave physics, the engineering of radio. The argument here is actually, well, it's quite unsettling in a good way. The argument is that digital isn't new at all, and that the smartphone in your pocket isn't some clean break from history. It's actually just the latest version of a smoke signal.
That is exactly the thread we are going to pull today. Because if you really look at the history of how humans move information, and it doesn't matter if it's a puff of smoke on a hillside in ancient China, a drumbeat in the Congo, or a 5G signal hitting your phone right now, the underlying logic, the actual physics of it, is identical.
So the mission for this deep dive is to trace that invisible thread. We are going to go all the way from Stone Age hackers to the invisible highway of the electromagnetic spectrum.
And we are going to break down the actual mechanics. I think a lot of people know that radio works, obviously. If you tune your car to 101.5, you hear music. But very few people can explain physically how a human voice travels through thin air without a wire.
We are going to debunk the magic and reveal the physics. So, looking at the roadmap we've got, we are starting way, way back, pre-electricity.
We have to. If you don't understand the drums, you simply cannot understand the internet. So we're starting with what I like to call the pre-modern hackers. We'll look at ancient drums, smoke signals, hydraulic systems. Then we move into the century of miracles, that really specific window where we went from Morse code to Marconi.
And then we get to the invisible highway, the electromagnetic spectrum itself.
Which is the medium for literally everything we do today. And finally, we're going to break down the nuts and bolts of AM and FM radio, how the voice actually gets inside the wave.
It sounds super technical, but looking at these notes, it's actually a deeply human story. It's about human ingenuity. So let's dive right into segment 1, the ancient roots of digital.
Let's do it.
The very first thing that jumps out at me from the source material is the definition of communication itself. I think we tend to overcomplicate it, We think about language, emotion, poetry, all the nuance. But mechanically, just from a physics standpoint, what are we actually doing when we communicate?
We are overcoming distance. That is the fundamental problem of the human experience. You have a thought in your brain, which is effectively just an abstract electrical pattern in your neurons. You need to get that exact pattern into another brain that is outside of your physical reach. To do that, you have to convert the thought into a physical signal that can actually propagate through space.
A physical signal. That seems to be the key phrase.
Right, because you can't just wish the thought across the room. It doesn't work that way. You have to disturb the physical environment, you have to disturb the air to make sound, or disturb the electromagnetic field with light or radio, or literally move a physical object. You are forced to encode your abstract information into physical reality.
And the sources argue that the logic of these ancient systems is completely identical to modern digital encoding.
It really is. Think about what the word digital actually means.
Hmm.
We tend to associate it with computers, silicon chips, glowing screens. But digital just means distinct, finite states, a 1 or a 0, on or off, yes or no.
So, okay, if I just wave my hand vaguely at you across the room, that's an analog signal. But if I give you a thumbs up, that's digital.
That is a perfect way to put it. A thumbs up is a binary state. It's either up or it's not. There is no ambiguity there. And our ancestors figured out very, very quickly that if you want to send a complex message over a long distance, you cannot rely on vague analog signals. You need digital precision.
Let's look at the first example in our stack here. Fire and smoke. We're talking about potentially a million years ago.
Yes, fire on hilltops. Now, it's important to clarify that simply lighting a fire is just a beacon. It's analog. It just says, I am here, or pay attention. But once you start manipulating the smoke, deliberately interrupting it, you are encoding information. The source specifically dives into the Great Wall of China.
This part completely blew my mind. I always thought of the Great Wall as just a wall, a really big pile of bricks designed to keep people out.
That is the standard tourist view. But strategically, it was a fiber optic cable made of stone. It was a high-speed data network.
How so? Walk me through the user experience of a guard stationed on the wall back then.
Imagine you are a soldier. You're stationed on one of these watchtowers. It's freezing cold. You're staring out at the horizon. Suddenly, you see a Mongol raiding party approaching in the distance. Now, if you just light a big fire, that tells the next tower down the line, hey, something is happening. But that is incredibly low-fidelity data. It's just a ping.
Right, it doesn't tell them if it's five guys looking for food or an entire invading army.
Exactly. But the sources describe a system where they actually manipulated the smoke to carry specific data. They burned wolf dung, specifically.
Wait, why wolf dung?
Because it creates this very dense, dark, thick smoke that doesn't easily disperse in the wind. And they would release it in controlled puffs. One puff might mean 100 enemies spotted. 2 puffs might mean 500 enemies. 3 puffs might mean over 1,000. Send the heavy cavalry immediately.
So they were literally encoding data into discrete packets of visual information. That is binary. That is digital.
It is. And the most brilliant key here is the relay network aspect. If you are the guard on Tower A, you signal Tower B. The guard at Tower B sees your signal. He doesn't have to sit there and interpret it or run to the Capitol on foot or write a physical letter. He acts as a repeater. He immediately duplicates the exact same signal to Tower C.
So you could transmit a highly specific data packet like invasion, 500 troops across thousands of kilometers in a matter of hours.
In a world where the absolute fastest travel speed was a horse, that is effectively light-speed communication. It travels as fast as the soldiers can physically see the smoke and react. It is the exact same architecture as a Wi-Fi repeater jumping a signal from the router in your living room to your bedroom.
It's just incredible to think about it that way. We think of networks as this modern invention, but they built a physical network out of stone and wolf dung.
Ingenuity born of pure necessity.
Yeah.
But of course, smoke has a pretty severe limitation. It's visual.
Right. You have to have line of sight. If it's foggy, the entire network goes down. If it's nighttime, smoke obviously doesn't work, so you have to switch to fire, which is way less precise to control in discrete puffs.
So humans moved to audio. The notes here mention the talking drums of Africa.
I have definitely heard of this, but I always just assumed it was basically Morse code. Like, tap, tap, tap meant H, tap, tap meant E.
It is actually vastly more sophisticated than Morse code. This is such a beautiful example of how human culture and physics intersect. In West and Central Africa, going back to around 4000 BCE, they developed a system using these massive hollowed-out slit drums.
And the key to making this work is the language itself, right?
Correct. Many African languages in that region are tonal. In English, pitch adds emotion or intent. If I raise my voice at the end of a sentence, it sounds like a question. But it doesn't change the actual dictionary definition of the words I'm using. In tonal languages, the pitch is the definition. A high-pitched sound might mean father, while the exact same phonetic sound at a low pitch might mean snake.
So the drummers weren't spelling out words letter by letter at all.
Not even close. They were mimicking the actual speech. They built these incredible drums that could produce 2 very distinct tones, usually a male tone, which was low, and a female tone, which was high. By striking different parts of the drum, they would literally play the tonal melody of the spoken sentences.
Well, wait, wouldn't that be incredibly ambiguous? I mean, surely lots of different phrases have the exact same up and down melody, like make me lunch might sound identical to watch the dog.
That is the genius part of the system. To solve that ambiguity, to do what we would call error correction in computer science. They used massive redundancy. They wouldn't just drum a short phrase like, come home. That's way too short. The melody could easily be confused. Instead, they would drum a long, standardized poetic phrase, something like, the little bats fly home to the branch in the evening.
Oh, wow. That is literally poetry functioning as encryption.
And compression, yes.
Yeah.
It's a beautifully long phrase that has a completely unique melodic signature. It simply couldn't be confused with anything else. When the neighboring village heard that specific rhythm and pitch combination floating through the jungle, they knew exactly what it meant without any doubt.
And again, we see this repeater concept showing up.
Yes, absolutely. A village would hear the drum message say it's a birth announcement or maybe a warning about a predator, and they would realize, okay, this isn't meant for us, this is heading for the capital. And they would immediately turn to their drums and bang it out to the next village down the line. The source material notes that messages could travel 100 kilometers in under an hour.
That predates telegraph architecture by millennia. It's an acoustic internet.
It really is an internet. You have your nodes, which are the villages. You have a transmission medium, which is the sound waves traveling through the air. And you have a strict protocol, which is the poetic drum language.
Okay, now here is where it gets really interesting for me. The hydraulic telegraph. 480 BCE. I read this in the notes, and it sounds like something straight out of a steampunk novel.
It is incredibly ingenious. This comes to us from the Greek historian Polybius, and it solves a huge, glaring problem with smoke signals. Smoke signals, as great as they are severely limited in vocabulary. You can really only agree on a few preset meanings. Danger, all clear, send help.
Right, you can't have a nuanced philosophical debate via smoke signals. You can't send a complex, unprecedented order like, send 50 ships to the eastern harbor at exactly dawn tomorrow.
Exactly. You can't send arbitrary text. You're stuck with a drop-down menu of 3 options. Polybius describes a system designed to solve this exact problem using water and gravity.
Walk us through this one. I'm trying to really visualize the physical mechanics of it.
Okay, imagine 2 separate hilltops, miles apart. On each hilltop, you have a really large jar. These jars are identical. They are precision engineered by potters to be exactly the same size and volume, and they are filled to the brim with water.
Okay, so we have synchronized hardware on both ends.
Precisely. Now, inside each jar, floating on the water, there is a cork float. And attached to that cork float is a tall vertical stick. On that stick, written top to bottom, are different codes, messages, or letters of the alphabet.
So it's like a ruler with letters carved into it sticking out of the jar.
Exactly like that. Now, both jars also have a distinct tap or a drain hole right at the bottom. The system works like this. The sender, who wants to transmit a message, raises a torch to signal across the valley, hey, get ready. The receiver on the other hill sees it and raises their torch to say, I see you, I'm ready. Then at the exact same moment, they both lower their torches and immediately pull the plug on the drain holes.
So the water starts draining out of both jars at the exact same speed.
Right. And as the water drains out, the cork float starts to sink, which means the stick with all the letters on it starts to go down into the jar. It slowly passes a little sighting notch on the rim of the jar.
Oh, I see. So it's a clock. It's basically a water clock.
It is a highly precise water clock. When the water level drops to the point where the specific letter or code the sender wants to transmit hits that notch, the sender quickly raises their torch again.
And the receiver sees that second torch flash, instantly closes their drain, and then just looks at where the water level stopped on their own stick.
Precisely. If they synchronized perfectly, if they opened and closed those taps at the exact same moment, the water level in the receiver's jar will be pointing to the exact same letter as the sender's jar.
That is just wild. They're using the steady, predictable flow of water as a timer to synchronize a pointer across miles of open terrain.
It is massively significant in the history of communication because it's one of the very first times information was encoded as a measurable, variable physical quantity. In this case, the water level. It's not just a simple on or off like a beacon. It's a sliding variable measurement used to convey specific digital data.
It feels like a massive Rube Goldberg machine, but the notes say it actually worked.
It worked extremely well enough that they used it to coordinate entire naval fleets during the Punic Wars. It gave them a massive tactical advantage.
Wow. Okay, moving forward in time, we get to the optical networks of the 18th century, and the notes literally call this the Internet of the 1790s, the optical semaphore.
Claude Chappie's network. This is really the absolute peak of mechanical communication before electricity came along and ruined all the fun. Imagine a vast network of stone towers, spaced about 10 to 20 kilometers apart, stretching all across the French countryside.
And instead of fires or water jars, they have these giant robot arms on the roof.
Yes, these massive wooden arms, painted pitch black so you could clearly see them silhouetted against the sky. They were incredibly complex. They had articulated joints, basically shoulders, elbows, and wrists. By moving those arms into different specific angles, the operators could create 196 distinct geometric positions. 196 positions. That's a massive amount of data. That's a huge alphabet to work with. It's effectively a full byte of data per symbol. They had thick code books in every tower, where one specific shape might mean the word "the," another shape meant "general," another meant "advance," or they could just spell things out letter by agonizing letter if they had to.
And what was the speed like?
It was grueling but fast. Operators would sit up at these drafty towers all day with telescopes, just staring at the previous tower down the line. As soon as they saw the giant arms move into a position, they would crank their own levers and replicate that exact movement on their own tower for the next guy to see. The source notes say a message could travel from Paris all the way to Toulon, which is about 750 kilometers in just 15 minutes.
15 minutes to cross an entire country in the 1790s. That is insane speed. That is faster than a steam train would be 100 years later.
Napoleon relied on it heavily for military coordination. Just think about the sheer asymmetric advantage they gave him. While his enemies were still writing letters and sending messengers on horseback, a process that took literal days to deliver a single order, Napoleon was dynamically coordinating troop movements across the entire country in minutes. It was a massive, massive strategic advantage.
It's amazing to think about. We look at these old stone towers in Europe today and think they are just quaint ruins, but at the time, that was bleeding-edge IT infrastructure.
And your reaction earlier, comparing it to a mechanical internet, is spot on. It had actual bandwidth limits, it had measurable latency, it had encoding protocols, it even had administrative overhead. It was a network.
So we have smoke, we have drums, we have water, and we have giant mechanical arms, all brilliant. But they all share a fatal limitation. They rely on line of sight, or they are bottlenecked by the speed of sound.
Correct. They were ultimately limited by the hard physical constraints of their medium. The semaphore doesn't work at night, no matter how hard you try. It goes completely offline in a fog storm.
Which brings us perfectly into segment 2. The chain of scientific progress. This is the big transition from mechanical to electronic.
This is a really specific 80-year window, roughly from the 1830s to the 1900s, where the entire world changed completely. And it's really important to emphasize what the notes point out here. This was deeply cumulative. It wasn't just one lone genius waking up and inventing the modern world. It was a relay race.
Let's meet the runners in this race, then. First up, Samuel F.D. Morse.
Morse. 1837. Now, the breakthrough here wasn't actually just the code itself. It was the physical proof that information could be reliably encoded as electrical pulses sent over long copper wires.
Because before this, electricity was basically just a novelty, right? A parlor trick to make a dead frog leg kick in a laboratory.
Exactly. It was magic. Morse showed that you could tame it and control it. He created a variable-length binary code, the famous dots and dashes. A dot is defined as 1 unit of time. A dash is 3 units of time. Now, I want to pause on the variable length part because the notes highlight this as a specific moment of genius that we still use today.
It absolutely is. Morse didn't just sit down and assign random clicks to random letters. He actually went down to a local printing shop and manually counted the pieces of movable type in the typesetter's boxes. He wanted hard data on which letters were used the most in the English language.
And he found that the letter E is the most common.
Right. So in Morse code, E is just a single dot, the shortest, easiest possible signal to send. T, another common letter, is a single dash. But a rare letter, like Q, gets a long, complex code, dash, dash, dot, dash.
That is literal data compression.
It is. He optimized the entire code for maximum transmission speed and efficiency over the wire. It is the exact same underlying logic used in MP3 audio files and ZIP files today. He was doing advanced software engineering decades before computers even existed. And he built the first true electronic network.
Baltimore to Washington, D.C., 1844. That was the pivotal moment when human communication finally detached from physical transportation. You didn't need a horse anymore. You didn't need line of sight. You didn't need good weather. You just needed a wire.
But wires have their own problems. They are incredibly expensive to lay down, and, crucially, You can't run a wire to a ship moving in the middle of the Atlantic Ocean.
Which is exactly why the next runner in our relay race is so profoundly important. James Clerk Maxwell, 1864.
The source material literally calls him the wizard figure of this era.
Because he didn't build a machine, he didn't invent a gadget you could hold, he built equations. Maxwell looked at electricity and magnetism, which every scientist at the time thought were two completely separate phenomena, and he unified them mathematically. He proved they were two sides of the same coin.
And he made a massive prediction based on that math, right?
The biggest. His math predicted that if you oscillate an electric field, it automatically creates a magnetic field, which then creates an electric field, and so on, forever. He predicted self-propagating waves of energy that would travel through the void at the exact speed of light.
So he predicted the existence of radio waves before anyone on Earth had ever actually seen or detected one.
He made wireless communication conceivable theoretically before it existed physically. He basically stood up and said, "My math says this invisible ghost has to exist." He even predicted that visible light itself was just a high-frequency wave of electricity and magnetism.
That takes a staggering amount of confidence to just say, hey guys, my math says there are invisible waves flying all around us at all times.
It takes singular genius. But, as in all science, theory isn't enough. You need physical proof. And that's where Heinrich Hertz steps into the story, about 20 years later.
Right, 1887, Heinrich Hertz.
Hertz read Maxwell's equations and basically decided, I'm going to prove this is real. He built a device in his lab called a spark gap transmitter. It was very simple. He used high voltage to create a big, loud electrical spark between two metal nodes. And across the room, completely unconnected by any wires, he had a simple loop of wire with a tiny microscopic gap in it.
And what happened when he fired it up?
He turned on the main transmitter. Snap! A big, bright spark. And instantly on the other side of the room, a tiny, faint spark jumped across the gap in the receiving loop.
Spooky action at a distance.
Exactly. He proved physically that invisible waves of electromagnetic energy were generated by the first spark, traveled through the empty air of the room, and induced a current in the second loop. He confirmed Maxwell's math perfectly. He proved you could produce, transmit, and detect these invisible waves. That's why the global unit of frequency is named the hertz.
But the truly funny thing here is, Hertz didn't actually think it was useful for anything, right? I've heard he thought it was just a neat parlor trick.
There's a very famous quote attributed to him. When his students asked what the practical application of these amazing invisible waves was, he basically said, "It's of no use whatsoever. It is just a neat experiment that proves Maestro Maxwell was right." He was a pure theoretical scientist. He simply did not see the smartphone coming.
Enter the practical engineer, Guglielmo Marconi.
Marconi, 1895. Now, Marconi wasn't necessarily a better physicist than Hertz. He probably wasn't. But he had incredible commercial vision. He took Hertz's basic spark gap and he started tinkering. He added much taller antennas, he grounded the system to the Earth, he improved the sensitivity of the detectors, and he turned a laboratory curiosity into a viable commercial product.
And his crowning milestone was the transatlantic transmission.
1901. From Cornwall in England all the way to Newfoundland in Canada. This is the exact moment the world fundamentally shrank.
But wait, didn't all the leading scientists tell him this was literally impossible?
Oh, they laughed at him. They openly mocked him. Because the science of the time said that radio waves, just like visible light, travel in perfectly straight lines, and the Earth, as we know, is curved. They said if you shoot a radio wave from England, it's just going to shoot straight off the horizon into deep space and miss Canada entirely.
But it didn't miss.
No, it didn't. And this was honestly a massive lucky break for Marconi. The waves bounced. It turns out the atmosphere isn't just empty air. High up, there is a thick layer of charged particles called the ionosphere. The low-frequency radio waves Marconi was using hit that ionosphere and reflected back down to Earth, effectively curving around the curvature of the globe.
Wow. So when Marconi picked up that faint signal, it was the letter S in Morse code,
Yeah.
right? Across the Atlantic, everything just changed overnight.
It meant you could finally talk to a ship in the middle of a raging ocean storm. It meant you could broadcast urgent news to an entire continent instantly. It broke the boundaries of physical geography.
Now, we definitely have to address the deep dive point on credit here from our notes. Marconi gets the fame, he gets the Nobel Prize, his name is everywhere. But there's another name that constantly comes up in this debate. Nikola Tesla.
Yes, and the source material is very careful and specific about this. There is a long-standing controversy. Tesla had earlier, established patents for key radio technologies, specifically the resonant tuning circuits that actually allow you to filter out noise and tune a radio to a specific frequency. Without that, radio is just a wall of static.
So if we use an analogy, Tesla designed the internal combustion engine, but Marconi built the first working car and drove it.
That's a very fair and accurate way to put it. In fact, in 1943, which is tragically just a few months after Tesla died in poverty, the U.S. Supreme Court actually intervened and restored several of Tesla's core radio patents. They effectively ruled that he had priority on the foundational tech. So historically, Marconi gets the credit for the incredible public demo, but Tesla gets the credit for the underlying foundation. Both are absolute giants in the field.
Okay, so we've gone from ancient smoke signals on the Great Wall to transatlantic radio waves bouncing off the atmosphere. But what exactly is this stuff that's carrying the signal? We keep throwing around the word waves.
This brings us perfectly to segment 3, the highway, the electromagnetic spectrum itself.
The highway. I really like that framing. So what are these waves actually made of? If I could hold one, what is it?
They are oscillating electric and magnetic fields. They are pure, massless energy propagating through empty space. And the one universal constant, the absolute unbreakable speed limit of the universe, is that they all, every single one of them, travel at the exact speed of light.
So wait, radio waves, visible light, X-rays, they're all exactly the same stuff.
Exactly the same. They are the exact same physical phenomenon. The only difference, literally the only mathematical difference between them is the frequency, just how fast they are wiggling up and down as they move forward.
Let's walk the spectrum then. The source lists them starting from low energy and going up to high energy.
Right. At the very bottom, the low energy end, we have radio waves. These have the lowest frequency and the longest wavelength. Some can be a millimeter long. Others, the really extreme ones, can be 100 kilometers long for a single wave cycle.
100 kilometers for a single wave, that's the distance between the crests.
Yes, mostly used for very low frequency military submarine communications, because they can penetrate deep into seawater. But generally, the radio waves we interact with are what we use for TV broadcasts, mobile phone networks, and MRI machines in hospitals. They're very low energy, which is fantastic because they pass right through the walls of your house and they don't damage human tissue.
Okay, moving up the energy ladder from radio.
Next, we hit microwaves. This is your Wi-Fi router, your GPS satellites, Bluetooth headphones, and yes, obviously, your microwave oven in the kitchen. They are shorter waves ranging roughly from a meter down to a millimeter.
Okay, dumb question time, but I have to ask. Why does the oven in my kitchen violently boil water and cook my food, but the Wi-Fi router sitting right next to it doesn't? They are both using microwaves.
It's a great question, and it's all about intensity and specific resonant frequency. The oven blasts about 1,000 watts of raw power at a very specific frequency that water molecules just love to absorb, causing them to vibrate and heat up. Your Wi-Fi router, on the other hand, emits a tiny, tiny fraction of a single watt. It's the difference between standing in a gentle, warm breeze and standing directly behind the exhaust of a 747 jet engine.
That makes perfect sense. Okay, what's next?
Infrared, literally meaning below red. This is what your TV remote uses to change the channel. It's also what we feel as ambient heat. When you look through thermal imaging goggles, you are just seeing infrared light radiating off warm bodies.
And then we hit the tiny slice we actually know best.
Visible light. It's actually a shockingly tiny, narrow sliver of the entire spectrum. The colors we see every day, red, green, blue, are literally just our brain's interpretation of different frequencies of electromagnetic waves.
That fact always profoundly blows my mind. The only physical difference between the color red and a Wi-Fi signal is just the frequency of the wiggle.
That's it. Human eyes are just organic antennas, evolutionarily tuned to receive that one specific narrow frequency band. If our eyes were tuned differently, we could literally see the Wi-Fi beams bouncing around our living rooms.
Okay, what happens when we go higher, above the color violet?
Now we enter ultraviolet. This is where the energy level gets high enough to start doing actual physical damage. UV rays have enough raw kinetic energy to knock electrons right off of atoms. They cause sunburns. If you get too much, they can directly damage your cellular DNA. But we also harness them for good, like water sterilization and checking the security features on banknotes.
And going higher still.
X-rays, extremely high energy. They have so much energy, they just pass completely through soft human tissue, like it isn't even there, which is exactly why we use them for medical imaging. But they get stopped by dense calcium in bones.
And the absolute top of the ladder.
Gamma rays. These are produced by violent radioactive decay, supernovas, and nuclear explosions. Extremely dangerous. Unimaginably high energy. We do carefully use them in targeted cancer therapy to destroy tumors, but you absolutely do not want to be anywhere near them otherwise.
So this raises a really practical question from the outline. Why do we use radio waves for our communication networks? Why not communicate via gamma rays? I mean, wouldn't they carry way more data because the frequency is so incredibly high?
It's true they could carry immense bandwidth, but they all travel at the same speed, light speed, so they aren't any faster at getting from point A to point B. There are two main reasons we stick strictly to the radio and microwave bands. First, as we just covered, is biological safety. You really don't want your new cell phone emitting highly ionizing gamma radiation that shreds your DNA every time you check your email. Gamma rays are lethal.
Yeah, that's a pretty solid consumer safety reason. Here's the new smartphone. It doubles as an actual death ray.
Exactly. Bad for marketing. The second reason is signal propagation. Radio waves are incredibly fantastic at passing through the Earth's atmosphere, bouncing off the ionosphere, passing right through brick buildings, and ignoring heavy fog. Visible light is great for fiber optics, but in the open air, it gets blocked by a single piece of paper or a thick cloud. Gamma rays are incredibly hard to generate, and even harder to safely detect without massive, heavy lead shielding. Radio is just the perfect Goldilocks zone for us. It's super easy to generate, it's safe for biology, and it travels beautifully through our specific environment.
So we have the highway built. Now we need to figure out how to actually pack the suitcase. How do we put human information onto these invisible waves? This is segment 4, signal types.
Right. You have the wave, which we call the carrier. But a steady, unchanging wave conveys absolutely no information. It's like staring at a blank sheet of white paper. You need to write on it. You need to modulate it. And historically, there are two main ways to do this: pulse and continuous wave.
Pulse seems much simpler. It sounds exactly like the digital approach we talked about earlier.
It is. Think of it as simply switching the wave on and off in a pattern, or pulsing it.
Like Morse code over the wire.
Exactly like Morse. Morse is the classic pulse signal. The carrier wave is either blasting out energy, a dot or a dash, or it's completely silent. There is no middle ground.
The notes have a specific classic example here, SOS.
Right, dot, 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 dash, 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 dot, dot, dot. The actual information isn't the wave itself. The information's entirely contained in the timing and pattern of the pulses.
So what's the big advantage of this? Why do we still use pulse-like binary logic for modern fiber optics and the entire global internet protocol?
Noise resistance. This is absolutely crucial for modern tech. Let's use an analogy. Imagine you were standing across a really crowded, noisy, smoky room, and I'm trying to send you a secret signal with a handheld flashlight.
Okay, I'm picturing it.
If I try to signal you by varying the brightness in tiny, subtle increments like, okay, a dim light means hello, a slightly brighter light means how are you, and a medium light means run, you are going to completely miss the message. The smoke in the air and the ambient light from the room will totally confuse your eyes. You won't know if I dimmed the flashlight or if some smoke just drifted in front of it.
Right, but if you just flash it hard on and then completely off if,
You will see it clearly every single time. Even if the light is super faint, even if the smoke is really thick, you can always confidently distinguish there is a light from there is no light. That is the power of binary. That is why digital systems are so incredibly robust. As the signal travels and gets weak, a repeater station can look at it, easily determine what is a 1 and what is a 0, and regenerate a brand new, perfectly clean signal.
wow, okay. But then there's the other major method, continuous wave. The analog approach.
This is a very different philosophy. The wave never stops. It persists constantly. But to send data, we continuously vary a property of that wave, usually the amplitude of the frequency, to perfectly mirror the source signal.
So instead of chopping the wave up into blocks, we are actively warping it in real time.
Warping is a very good word for it. We might warp its height or warp its speed. This is exactly how old-school analog radio works.
But the massive disadvantage here is noise.
A huge, sometimes fatal disadvantage. If random static, say, from a lightning storm crashes into an analog wave, it physically distorts the shape of that wave. And since the information you are trying to send is the shape of the wave, the information itself gets permanently corrupted. You hear that exact corruption as a hiss or a crackle on your car radio.
So to summarize, pulse is discrete, it's binary, and it's incredibly tough against noise. Continuous wave is smooth, it's analog, but it's very sensitive and delicate. Okay, so we've got the suitcase packed. Now let's talk about the absolute most common thing we have historically packed in there, the human voice. Segment 5, the magic of radio.
This is the really fun part where we finally break down the actual physical mechanics of how AM and FM radio broadcast actually work.
The outline starts with a really interesting challenge that I never thought about. Why can't we just transmit a human voice directly? Like, if I hook up a standard microphone directly to a giant metal antenna, why doesn't my voice just fly out as a radio wave?
This is strictly a matter of physics and required antenna size. Human voice frequencies are very, very low, roughly ranging from 300 hertz up to about 3,400 hertz.
And as we learned earlier, a low frequency means a very long wavelength.
A massively long wavelength. If you plug the average frequency of your speaking voice right now into the standard wave equation, the resulting wavelength is literally hundreds of kilometers long.
And the general rule of thumb in radio engineering is that your transmitting antenna needs to be roughly half the size of the wavelength you are trying to send.
Roughly, yes, to resonate efficiently. So if you genuinely wanted to transmit your raw voice directly as an electromagnetic wave, your physical metal antenna would need to be somewhere around 100 kilometers tall.
Which is obviously wildly impractical for a pocket device. Or anything, really.
Slightly impractical, yes. So engineers came up with a brilliant solution, the carrier wave. Instead of sending the voice directly, we generate a very high frequency wave, say 100 megahertz. At that high frequency, the wavelength is only about 3 meters long. That means you only need an antenna that is 1.5 meters long, which easily fits on a car or in a handheld radio.
I really love the analogy the notes use here. The carrier wave is the vehicle. The voice is just the passenger.
Yes, the vehicle, the high-frequency wave, is perfectly designed to travel smoothly on the highway of the open air. The passenger, your low-frequency voice, just sits comfortably inside. The carrier wave literally carries the voice information across the void.
So let's physically walk through the 5-stage journey described in the notes. Step 1, sound to electrical.
That's the microphone's job. You speak. Your vocal cords create air pressure waves. Those waves hit a tiny diaphragm in the mic, and that physical movement is converted into a fluctuating electrical voltage. So now, your acoustic voice is an electrical signal traveling down a copper wire.
Okay, step 2, carrier generation.
Deep inside the radio transmitter building, there is an electronic oscillator. It's just sitting there constantly creating that perfectly steady high-frequency wave.
Yeah.
It's building the empty truck, waiting for cargo.
Step 3, modulation. The notes call this the magic step.
This is where we finally put the passenger inside the truck. We modulate, which just means to modify or change the carrier wave based exactly on the fluctuating voice signal. We imprint or impress the voice data onto the high-frequency carrier.
Step 4, transmission.
The giant tower antenna takes that modulated carrier wave and blasts it out into the atmosphere at the speed of light in all directions.
And finally, step 5, reception and decoding.
Your car radio antenna catches a tiny fragment of that wave. The tuner circuit filters out all the other stations to select the specific frequency truck you want. Then, the demodulator circuit literally kicks the passenger out of the truck. It strips away the high-frequency carrier wave, extracts the original low-frequency voice signal, amplifies it, and pushes it to a speaker cone, which turns it back into sound waves your ear can hear.
It is genuinely incredible that all of that complex physics happens instantly.
Well, light speed is very forgiving when it comes to human perception of time.
Now, you mentioned modulation. We have 2 main types that literally everyone knows from their car dashboard, AM and FM. Let's break down the battle of the modulations.
Let's start with AM. AM simply stands for amplitude modulation. In this method, to put the voice on the wave, we rapidly vary the height or the strength of the carrier wave.
So if I imagine the carrier wave as a series of ocean waves coming at me at a perfectly steady pace on a beach.
Right, the pace, the frequency never ever changes. But the height of those waves changes constantly. If you scream loudly into the microphone, the transmitter makes those ocean waves huge, 10 feet tall. If you suddenly whisper, the transmitter shrinks those waves down to tiny 1-foot ripples.
So if I were to draw a line connecting the very top peaks of all those waves, that outline, that envelope, perfectly matches the electrical pattern of my voice.
Exactly. That outer envelope is the actual signal.
What are the pros and cons of doing it this way?
Pro. It is incredibly simple, primitive technology. You can literally build a working AM radio receiver out of a rusty razor blade, some wire, and an earphone soldiers used to do it in trenches. Also, AM waves, because they are usually in lower frequency bands, tend to travel very far. They can bounce off the ionosphere at night, and a station in Chicago can be heard in Texas.
But the con, we mentioned it earlier.
Static. This is the big fatal flaw of AM. Think about a lightning strike miles away, or a spark plug firing in a car engine, or a faulty power line. All of those things emit massive random bursts of electromagnetic energy, spikes in voltage.
And since the entire AM system relies on reading the voltage, the amplitude, the height of the wave.
Your car radio receiver sees that random lightning spike hit the antenna, and it thinks, oh, the wave just got really tall. That must be part of the music signal. It dutifully interprets the electrical noise as a loud, jarring crash through your speakers. You cannot filter out the noise because, to the radio, the noise looks exactly like the signal.
Enter FM to save the day. Frequency modulation.
In FM, we change the rules completely. We absolutely do not touch the height of the wave. The amplitude stays rigidly constant. The waves are always exactly 10 feet tall no matter what.
So if the height never changes, where's the voice information hiding?
We vary the frequency instead. We vary the pitch, or the speed at which the waves arrive. Imagine the carrier wave is a giant metal slinky. When you scream loudly into the mic, we rapidly scrunch the slinky together. The waves come much faster, frequency goes up. When you whisper, we stretch the slinky out, the waves arrive slower, frequency goes down.
We are wiggling the timing of the waves, not the physical strength.
Correct. The voice is encoded in how compressed or stretched the wave is at any given microsecond.
And this somehow completely fixes the static problem.
Almost completely.
Yeah.
Because, as we said, random lightning strikes or electrical interference primarily affect the amplitude they add, chaotic height to the wave. But an FM receiver circuit is specifically designed to completely ignore the height. It acts like a clipper. It looks at the incoming wave and says, I don't care at all that the height is jumping up and down erratically. I'm only counting the horizontal spacing between the peaks.
It literally just slices the noisy tops off the wave and throws them in the trash.
It does. It just reads the timing. That's why FM sounds so crystal clear. It has much higher fidelity, which is why music moved to FM.
But because FM usually uses much higher frequencies to get that bandwidth, it has a much shorter physical range.
Right. High-frequency FM is strictly a line of sight. It has so much energy, it just punches straight through the ionosphere into space rather than bouncing back down to Earth like AM does. So the moment you drive your car over a steep hill or behind a large mountain, you completely lose the station.
So AM is for talk radio, news, and emergency broadcasts over massive long distances. FM is for high-fidelity music and local, clear broadcasting.
That is the ultimate engineering trade-off.
So what does this all mean for us today? We've gone from Polybius synchronizing water jars in ancient Greece to Marconi making sparks jump oceans, all the way to the complex FM tuner sitting in my car dashboard.
I think when you step back and look at the entire historical picture we've painted today, the summary is this. Every single step forward in this timeline was just humanity finding a slightly better, slightly faster way to vary a physical observable to encode meaning.
Whether that physical observable is the exact level of water draining from a clay jar,
Or the precise geometric position of a wooden arm on a French tower.
or the invisible amplitude of an electromagnetic wave flying through the sky.
It's all exactly the same thing. We are taking the intangible, abstract thing, our thoughts, our information, our data, and we are forcefully stamping it onto the physical world so we can throw it across the void of space to reach someone else's mind.
It connects us. It's the ultimate tool of empathy and coordination.
It genuinely defines us. We are the one species on this planet that absolutely refuses to be isolated by physical distance.
I really want to leave you, the listeners, with the final provocative thought from our outline today, because I read this and it really stuck with me.
It is definitely something to just sit and mull over. Right now, wherever you are listening to this, if you are driving in your car, sitting in your living room, or out on a jog, I want you to consider the empty air immediately around your body.
It looks completely empty. It feels like nothing is there.
But it is incredibly thick. It is absolutely thick with invisible carrier waves. There are thousands of private conversations, gigabytes of encrypted internet data, pop songs, news reports, and satellite signals passing right through your physical body at the exact speed of light at this very second.
We are literally walking through a dense, chaotic fog of human information.
A fog that we can only perceive if we happen to have the exact right tuner, a smartphone, a radio, a TV antenna, to extract that one specific signal from the overwhelming noise. We are swimming in an infinite sea of communication that is completely invisible to our biological senses.
That is, honestly, it's slightly terrifying when you picture it, but mostly it's just awe-inspiring.
I think it's beautiful. It's the culmination of everything we've talked about today.
Well, next time you pull that glass rectangle out of your pocket, just take a single second to appreciate the thousands of years of physics and struggle making it work. It's not magic. It's actually so much better than magic.
It's waves.
Thanks for diving in with us today. We'll catch you on the next deep dive.
Goodbye, everyone.
I want to start today by asking you to just look at your phone, just hold it in your hand for a second.
Yeah, take a good look at it.
It feels like this really solid object, right? I mean, it's glass, it's aluminum, maybe you've got some plastic case you bought online on it.
Probably a screen protector that's a bit cracked.
Right, exactly. But if we really look at what that device is doing right now, like pulling this audio stream out of the literal ether, syncing your emails, updating the weather app, it stops feeling like a rock, and it really starts feeling like magic.
It's the Arthur C. Clarke principle, right? Any sufficiently advanced technology is indistinguishable from magic.
Yes.
But the funny thing is, as soon as you peel back that layer of magic, you don't find spells, you find physics, you find very rigid, very heavy industrial infrastructure.
And that is exactly where we are going today. I've been completely buried in this stack of research for today's deep dive. It's all about the physical infrastructure of the information age. And man, it completely changed how I look at the world.
It'll do that, yeah.
Because we usually talk about the cloud like it's this, I don't know, this fluffy, ethereal place where our data lives.
Up in the sky somewhere.
Right up in the sky. But the sources we're diving into today make it painfully clear. The cloud is not a cloud.
Not even close.
It's underwater glass cables, it's copper wires literally digging into the dirt, and it's invisible waves bouncing off the upper atmosphere.
It's a massive machine. Really, it is arguably the largest, most complex single machine humanity has ever built. It spans the entire planet, and it even extends up into orbit.
Yeah.
And yet we just treat it like a utility. We expect it to work exactly like gravity.
So our mission today for this deep dive is to basically break the spell. We are going to deconstruct the machine. And the research creates this really perfect three-part structure. It's almost like a geological dig.
I like that analogy.
Yeah, so we're going to start at the top with the invisible stuff, right? Radio and wireless. Then we're going to dig down into the ground to talk about the transmission media. So your copper and your fiber optic cables. And finally, we're going to shrink ourselves all the way down to the atomic level to look at digital logic. The actual microscopic switches that do the thinking.
It's a journey straight through the stack, from the macro waves that literally wrap the Earth all the way down to the nanometer, switches inside a tiny piece of silicon.
And the big driving question through all of this thing I want to keep bringing us back to is really the struggle against entropy.
The big enemy.
Exactly. Like, how do we actually move a complex idea, a Shakespeare sonnet or a cat video, across the entire planet without it just turning into garbage?
Well, that right there is the fundamental problem of communication engineering. The universe inherently wants to turn order into chaos. It wants to turn your nice, clean signal into random noise.
Right.
So every single piece of technology we're going to discuss today is essentially a weapon in that war against noise.
So let's start the war. Let's start with the air around us. Section 1 here is radio.
The wireless world.
Now, the sources define radio much more broadly than just, the thing sitting in your car dashboard. We are talking about a massive chunk of the electromagnetic spectrum here.
We are. In strict physics terms, radio is just the transmission of information via modulated electromagnetic waves. It sits at the very lower end of the spectrum compared to, say, visible light.
Yeah.
We're generally talking about frequencies starting from about 3 hertz, which is incredibly low.
Right.
That's basically a wave that is thousands of kilometers long up to about 300 gigahertz. And those are tiny millimeter-sized waves.
And the real superpower here is speed, right? It's the speed of light.
Exactly. 3 times 10 to the power of 8 meters per second.
Which is
roughly 300,000 kilometers every single second. So for any communication happening just here on Earth, it is effectively instantaneous.
I was looking at the pros and cons list in the research, and the pros of radio seem pretty obvious. Mobility is the massive one.
Right. You can't have a smartphone if you have to be physically plugged into a wall socket.
Yeah. Exactly. Radio breaks that physical tether. It allows for ubiquitous connectivity. It's also just incredibly efficient for broadcasting. If I want to speak to 1 million people in a city, I don't need to run 1 million individual wires to their house.
Right. You just put up one really tall tower.
Yeah.
Pump a lot of energy into it, and everyone listens.
And there is a really massive, but here, the research highlights a concept that I hadn't really connected to radio before. The tragedy of the commons.
Ah, yes. This is the defining constraint of all wireless technology. The spectrum is a finite resource. It's like a shared public park.
Right.
If you and I are standing in the same room and we try to shout different messages at the exact same pitch, the same frequency at the exact same time, neither of us will be understood. We just create interference.
It just becomes noise.
It becomes total garbage.
Yeah.
And because we can't just manufacture more spectrum,
Mhm.
I mean, the laws of physics gave us what we have, and that's it. We have to regulate it aggressively.
Right, you can't just set up a rogue cell tower.
Exactly. That's why you can't just start your own TV station tomorrow from your backyard. You need a government license to occupy that specific lane on the highway.
Then there's the security aspect of it. The notes describe radio as a, quote, public shout.
I think that's a really good way to put it. A wire is a private whisper. It goes from point A directly to point B, but an antenna radiates energy in all directions,
Everywhere.
everywhere. If you're using Wi-Fi, your private emails are literally flying through the walls into your neighbor's apartment, out into the street, maybe even up to a drone flying overhead.
That's the only reason my neighbor can't just open his laptop and read my emails is encryption, right? It's not the physics protecting me.
Correct. Physically, they have the exact same signal your router does. Mathematically, though, they hopefully can't understand it because it's scrambled.
Okay, so the third disadvantage, and this is where we really start getting into some cool physics, is attenuation. The signal just dies off.
And it dies off much faster than most people realize. It follows the inverse square law.
I really want to unpack that law because the name sounds super intimidating, but the concept is actually pretty intuitive once you visualize it.
It really is. Imagine a balloon. When you blow it up, the surface area of the rubber stretches out right.
Yeah.
Radio waves expand outwards as a sphere just like that balloon. As that sphere gets bigger and bigger, the initial energy is spread out over a much larger area.
Right, so the energy gets diluted.
Exactly.
Right.
The math says that if you double your distance from the transmitter, you don't get half the signal strength like you might expect. You get 1/4.
Okay, so if I move from, say, 1 meter away to 2 meters away, I only have 25% of the power left. And if I step back to 4 meters away...
You are down to 1/16 of the original power.
Huh.
The signal strength just completely falls off a cliff.
Wow.
And this is exactly why 5G cell towers have to be literally everywhere. High-frequency signals attenuate so fast that they can barely make it down the block before they fade into the background noise.
But the notes also show that not all radio waves travel the same way. This was actually my favorite part of the wireless research, the propagation modes. It turns out radio waves have totally different personalities depending on what their frequency is.
Yeah, we usually categorize them into 3 main behaviors. You have ground waves, sky waves, and line of sight.
Let's start with ground waves. These are the low frequencies. The sources say they literally hug the curvature of the Earth. How is that even possible? Because I thought electromagnetic waves like light traveled in straight lines.
Light does travel in straight lines, but long radio waves, and we're talking about wavelengths of hundreds of meters, here they interact with the Earth's surface.
Okay.
Through a physics process called diffraction, the wave effectively grabs onto the conductive surface of the Earth and curves right along with it.
So if I'm broadcasting a very low frequency signal, I can reach someone well beyond the physical horizon.
Yes, absolutely. Ground waves can travel for hundreds of kilometers. They just crawl right over hills and dip down into valleys. But there's a trade-off. You can't send much actual data on them. Low frequency inherently means low bandwidth.
Right. Then we have the sky waves. And this is where that magic feeling really came back for me when I was reading. The research describes this phenomenon where AM radio stations can suddenly be heard thousands of miles away, but only at night.
Ah, the famous nighttime skip. This is a beautiful interaction between radio waves and the sun.
So help me understand the mechanism here. We're dealing with the ionosphere, right?
Right. The ionosphere is a layer of our atmosphere starting about 60 kilometers up where the air is ionized, meaning it's absolutely full of charged particles.
And the notes mention very specific layers within that, the D layer, the E layer, and the F layer.
Exactly. Now, during the day, the sun is constantly blasting the Earth with ultraviolet and X-ray radiation. This intense radiation hits the upper atmosphere, and it creates a very dense, low layer of plasma called the D layer.
And the notes say the D layer is a radio killer.
It is a giant sponge. Medium frequency signals like your AM radio, they go up, they hit that dense D layer, and they just get completely absorbed. The radio energy just turns into heat.
Right.
So during the daytime, your signal goes up and it dies. You only get to hear the local ground wave.
But then the sun sets.
The sun sets, the solar radiation stops.
Yeah.
And the D layer, which needs that constant solar radiation to exist, simply fades away. It dissipates.
Wow.
But the layers above it, the E and the F layers, they're much higher up, and they stay ionized for a lot longer.
So the sponge is essentially gone, exposing a mirror behind it.
That is a perfect analogy.
Yeah.
The signal travels up, passes right through where the D layer used to be, and hits the F layer. And because of the severe difference in the refractive index of that plasma, the radio wave is bent. It's refracted so sharply that it comes right back down to Earth.
It literally bounces off the sky.
It skips. It can bounce from the ionosphere down to the ocean, bounce back up to the ionosphere, and finally land in a radio receiver in a completely different hemisphere.
That is just incredibly cool. But I guess we can't run the modern internet on skipping skywaves, right? We need something a lot more reliable and faster. Which brings us to the third mode, line of sight.
This is the modern workhorse, VHF-UHF microwaves. This is your FM radio, TV, Wi-Fi, 5G, and GPS.
And as the name implies, it travels in a perfectly straight line.
Exactly. No hugging the ground, no bouncing off invisible clouds. It works exactly like a laser pointer. If your receiver can physically see the transmitting tower, you can get the signal.
The problem, obviously, being that the Earth is a giant ball.
A sphere with a radius of about 6,400 kilometers. If you stand on the beach, looking at the horizon is only about 5 kilometers away from you. Anything beyond that is physically blocked by the planet itself.
Which perfectly explains the infrastructure we see all around us, right? We build tall towers just to push the horizon further back.
And ultimately, we build the tallest towers of all, satellites. A satellite is really just a line-of-sight relay station that is high enough up to see over the curve of the Earth.
So that's the air. It's incredibly fast, it's totally flexible, but it's crowded, and it constantly fights the geometry of the planet. If we want to move serious data, like the actual petabytes of data that run the global economy, we have to get out of the air and go into the ground.
We need transmission media, the physical highway.
We really have two main characters in this part of the story. Copper and optical fiber, or as I kind of like to think of them, the electron and the photon.
That is the absolute fundamental distinction. Are we pushing electricity or are we pushing light?
Let's start with copper. It's definitely the old guard. We're talking telephone lines, Ethernet cables, coaxial cables. It's been running the world basically since the telegraph.
And copper is a genuinely fantastic material. It's a great conductor. It's highly ductile, which means you can easily stretch it into thin wire. And we know exactly how it works.
Right.
We send information by varying the voltage of an electrical current that travels through the metal lattice.
And it has one massive advantage that fiber optics still can't match, right? Power.
Power over Ethernet, or PoE. You can use the exact same copper cable to send the YouTube video data and the actual electricity required to power the screen.
That's so convenient.
It is. Fiber is just glass. It cannot conduct electricity at all. So with copper, you only need to run one single wire through the ceiling to power your security camera or your Wi-Fi access point.
But reading the research, the cons list for copper is getting longer every single year, and the first big one is resistance.
Yeah, electrons actually have mass. When you try to push them through a solid wire, they physically bump into the copper atoms. That creates friction, heat, and resistance. It means the electrical signal gets weak very quickly.
We're back to attenuation again.
Exactly. In high-speed data cables, like a standard Cat6 Ethernet cable, the signal degrades to unusable levels after just 100 meters. If you need your network to go 101 meters, you have to buy a repeater, a power device just to boost the signal. And that is very expensive infrastructure to maintain at scale.
And then there is the interference issue.
Yeah.
Because a copper wire is basically just a giant antenna, isn't it?
It absolutely is. If you run a copper data cable right next to a high-voltage electrical power line, the magnetic field radiating from that power line will physically induce a rogue current inside your data cable.
So it literally injects noise into your data.
It totally corrupts the data. We try to fight this by twisting the pairs of wires inside the cable. That's why it's literally called twisted pair cable, because the twisting helps cancel out the incoming interference, but it's never perfectly clean.
And that leads right into the security risk, because induction works both ways, right?
Right. If you can induce noise into the cable from the outside, you can also read the signal out of the cable from the outside. A skilled spy doesn't need to physically cut the wire and splice into it.
Really?
No, they just need to place a sensitive sensor coil right next to the jacket of the cable. They can read the microscopic magnetic field changes and perfectly reconstruct the data stream without ever touching the bare copper.
Wow. Okay, so enter the modern challenger. Optical fiber, the speed human of the internet.
Fiber is a total paradigm shift. We are no longer sending heavy electrons. We are sending pulses of massless photons. Light. Usually we use near-infrared light with specific wavelengths like 1310 or 1550 nanometers.
I kept seeing those specific numbers in the notes. Why those exact wavelengths? Why not just use regular visible light that we can see?
Because glass, even ultra-pure manufactured silica glass, absorbs different wavelengths of light differently. It turns out there are these natural windows of transparency in the glass where attenuation is at its absolute lowest possible point.
Oh, okay.
So 1550 nanometers happens to be the perfect sweet spot where the light can travel the furthest possible distance without being absorbed by the glass molecules.
And when we say travel furthest, the difference compared to copper is just staggering.
Oh, it's a completely different league. With copper, you were struggling at 100 meters. With modern single-mode fiber, you can send a clean signal 80 to 100 kilometers before you need a repeater.
And what about the bandwidth?
Terabits per second. A single strand of glass, thinner than a single human hair, can carry more simultaneous data than a massive bundle of copper cables the size of your thigh.
Plus, I imagine it's totally immune to all that electromagnetic interference stuff we talked about.
Completely immune. Light doesn't care about magnets at all. You could wrap a fiber optic cable tightly around a massive high-voltage substation transformer, and the data signal won't even flicker.
But here's the part of the research that I really needed to sit with. The actual how of it all. Because my intuition naturally says that if I shine a flashlight into a clear glass tube, the light should just shine right out the sides.
Right, because glass is transparent.
Exactly, glass is see-through. So how on earth does the light stay trapped inside the cable for 100 kilometers without leaking out?
This brings us to the concept of total internal reflection. It is arguably the single most important physical principle in modern optics.
So let's visualize this for the listener. We have the fiber cable. It has a tiny center channel called the core and a slightly thicker outer layer wrapping it called the cladding.
Correct. And crucially, they're made of two slightly different types of glass with different refractive indices.
Refractive index being a measurement of how much the material slows down light passing through it, right?
Roughly, yes. It's a measure of optical density. The core has a higher index, so it's optically denser for the light, and the cladding has a slightly lower index.
Okay, so I shoot a laser beam straight down the core. It travels along until it eventually hits the wall, the boundary between the core and the cladding. The research outlines 3 specific scenarios for what happens the moment the light hits that wall.
Let's start with scenario 1, refraction. Imagine you are standing on the edge of a calm pond and you throw a heavy rock straight down into the water. What happens?
It just breaks the surface and sinks straight into the water.
Right. If the laser light hits the cladding boundary at a steep angle, it just passes straight through. It escapes the core and is lost in the cladding. We lose the data signal entirely. This is obviously bad.
Okay, scenario 2. We start changing the angle of the throw. We throw the rock more sideways across the pond.
Eventually, as you change the angle, you hit a very specific mathematical angle called the critical angle. In standard glass and air, it's about 42 degrees, but it varies depending on the exact materials.
And what happens at 42 degrees?
At exactly the critical angle, the light can't quite escape into the cladding, but it also can't quite reflect back into the core. It travels perfectly along the boundary. It literally skims the surface.
Still not very good for transmitting data, though, right? We need the rock to skip, not skim.
Exactly.
Yeah.
Here's scenario 3, total internal reflection. If the angle of incidence is shallower than that critical angle, so it's a very glancing blow against the wall, the boundary undergoes a sudden phase change in behavior. It stops acting like a transparent window, and it instantly acts like a perfect mirror.
And when you say perfect, you mean mathematically perfect.
I mean 100% reflection. The absolute best silver mirror sitting in your bathroom right now only reflects about 90 to 95% of the light that hits it. The rest is absorbed as heat. If we built internet cables using bathroom mirrors, the signal would be completely gone at a few kilometers. But total internal reflection is completely lossless. The photon bounces off the boundary with the exact same energy it had the moment before it hit.
So the light effectively just zigzags down the tube, bouncing billions of times, and it never loses any energy to the glass walls.
Exactly. It
Yeah.
is completely trapped by the fundamental laws of physics. As long as a construction crew doesn't bend the cable too sharply, which would force the light to hit the wall at a steep angle and let the light escape, that photon will successfully travel to the other side of the ocean.
That is exactly the hidden magic I was looking for. We've literally tricked light into staying inside a cage.
It's wonderfully elegant. There are 0 moving parts. It's purely just geometry doing the heavy lifting.
Okay, so we've covered the waves in the air with radio and the pipes in the ground with the cables. Now we really need to talk about the water flowing through those pipes, the information itself. This brings us right into the war between analog and digital.
The underlying language of the machine.
I feel like analog is a word we toss around a lot without ever really defining it. The research says analog is continuous. What does that mean in physical terms?
Analog is a direct physical representation of reality. Think of a classic vinyl record.
Hmm.
If you look closely at the groove under a powerful microscope, it is a continuous wavy line cut into the plastic.
Right.
That physical wave is a perfect analogy of the actual sound wave that hit the recording microphone in the studio. It is a continuous infinite curve.
So if I zoom in on a specific part of that wave, it's still just a smooth, continuous curve.
Infinite resolution. Between any two physical points on that smooth curve, there is mathematically always another point. It never breaks into discrete steps.
Digital, on the other hand, the notes describe as discrete.
Digital is a staircase. It's not a smooth, continuous ramp. We artificially chop the flowing information up into highly specific blocks, and in computing, usually just 2 blocks, 0 and 1.
Now, looking back at the history of all this, the whole world used to be analog. Early phone systems were analog. All broadcast TV was analog. Why did we go through the massive trouble of switching everything over? The research points to one highly specific enemy here: noise.
The noise problem is the ultimate Achilles heel of any analog system. Because in an analog system, absolutely everything on the wire is treated as the signal.
Give me a real-world example of that.
Imagine you're listening to an old analog cassette tape.
Hmm.
You hear the recorded music, but you also hear that constant background hiss.
The tape's dead.
Right, that static is just random microscopic magnetic variations on the physical tape. The tape player is dumb. He doesn't know the difference between the intended guitar solo and the random static. It happily amplifies both.
Right.
And if you make a copy of that tape onto a second blank tape, you perfectly copy the original static and you naturally add new static from the second tape.
The classic photocopy of a photocopy effect. It just gets blurrier and worse every single time you copy it.
Exactly. Noise accumulates instantly. You can never scrub it out. But digital is completely different. Digital possesses a superpower that we call noise immunity.
How exactly does that work?
Let's say we are sending a digital signal down a long copper wire. We establish a rule beforehand. We decide that 3 volts of electricity means a 1, and 1 volts means a 0.
Simple enough rule.
Now we send a perfect 3-volt pulse, which is a 1, but there's terrible interference on the line. Some random electrical noise gets injected. The signal physically arrives at the far end of the cable, not as a crisp 3 volts, but as, say, 2.8 volts.
So the signal is corrupted.
In an analog world, yes, entirely corrupted. But a digital receiver looks at that messy 2.8 volts and it just asks a very simple logical question. Is this incoming voltage closer to our rule for 3 or is it closer to 0?
It just rounds it up.
It says, okay, that's definitely a 1. It completely ignores the 0.2 volts of random noise. It reconstructs a brand new perfect 3-volt signal inside the machine. You can do this precise process 1 billion times, routing it through 1 billion different servers, and the text message at the end will be bit for bit mathematically identical to the message sent at the start.
That is quite literally why the internet can exist. You couldn't possibly have a global network bouncing around the Earth if the signal degraded a tiny bit every single time it hopped through a router.
Correct. The whole thing would devolve into static. But to get that magical immunity, we have to pay a serious price up front. We have to convert our beautiful, smooth, continuous analog reality into these rigid, blocky digital numbers.
Right, and this is the sampling and quantization process outlined in the notes. I want to spend a minute specifically on sampling because the underlying math here is fascinating. It introduces a guy named Harry Nyquist.
The Nyquist-Shannon sampling theorem. It is essentially the mathematical bridge between the real analog world and the digital computer world.
The theorem states that to capture any wave perfectly, you have to sample it, meaning you have to measure it at least twice as fast as its highest frequency.
Right. Think of a ceiling fan spinning rapidly. If you blink your eyes really slowly while watching it, the fan blades might look like they've stopped completely, or maybe even look like they're spinning backwards.
Yeah, I've seen that effect on video.
That is called aliasing. To see the actual forward motion correctly, your eyes have to take a sample blink significantly faster than the fan is rotating.
So applied to audio recording, humans can physically hear sound frequencies up to roughly 20,000 hertz.
So if we want to record an orchestra digitally, Nyquist's math explicitly dictates that we must sample the analog microphone voltage at least twice that rate, so 40,000 times every single second.
Which perfectly explains the global standard for CD audio, 44,100 hertz, 44.1 kilohertz.
Exactly. The engineers chose 44.1 kilohertz to completely cover the full 20 kilohertz range of perfect human hearing, plus a little bit of extra mathematical wiggle room for the physical electronic filters to operate smoothly. That 44.1 number wasn't just pulled out of thin air. It was strictly dictated by the theorem.
So that is step 1, sampling, which is essentially slicing up time into chunks. Step 2 is quantization, slicing up the actual value.
We have to measure the physical height of the sound wave at every single one of those 44,100 samples and assign it a specific number. But inside a computer, we only have a limited set of discrete numbers to choose from. This is what we call bit depth.
Like 8-bit versus 16-bit audio?
Right. In an 8-bit digital system like old Nintendo video game audio, you only have 256 possible volume levels from silent to maximum. So the computer has to forcibly round the exact height of the wave to the nearest available step.
And that rounding error creates a very specific kind of distortion, right?
Yes, it sounds very gritty and harsh. It's quantization noise. But if you upgrade to a 16-bit system, like a standard audio CD, you suddenly have 65,536 available levels. The mathematical steps are now so incredibly tiny that the human ear simply cannot distinguish them from a perfectly smooth, continuous line. We've successfully fooled our own biology.
So we've taken chaotic reality, we've chopped up into bits, and we've cleaned out all the random noise. Now we have to actually process it. We need a physical machine that natively speaks this blocky language of zeros and ones. This leads us to the final foundational layer of the stack, the hardware.
The transistor.
I feel like we hear this word constantly in the news, but we rarely actually stop to ask what it physically is.
It is objectively the most important technological invention of the 20th century. Without it, we simply do not have the modern world. Physically speaking, in modern computers, it's a MOSFET, a metal oxide semiconductor field effect transistor.
Which is an absolute mouthful, but
Yeah.
functionally speaking, it's just a switch, isn't it?
It's a switch with absolutely no moving mechanical parts. It generally has 3 active terminals. The source, where the electrons come in the drain, where the electrons go out, and the gate, which is the controller.
The garden hose analogy seems to be the standard go-to here in the notes.
It works perfectly. Imagine a standard garden hose. Pressurized water wants to flow from the tap of the source out to the yard the drain. But you are standing firmly on the middle of the hose. The flow of water is completely blocked.
That would be the off state.
Yes. In a MOSFET, the gate is your foot. When we apply a tiny electrical voltage to the gate terminal, it creates an invisible electrical field that effectively lifts your foot off the hose. It opens a conductive channel through the silicon. Current instantly flows. That state is on. That state is a 1.
And then you take that control voltage away.
The physical channel instantly collapses. The electrical current violently stops. That is the off state. That is a 0.
Now I have to ask the question that came up during the critique of our preliminary research notes. Why binary? Why are we completely stuck with just 0 and 1? Humans have 10 fingers. Human math is natively decimal. Why don't we build computers that natively use voltages representing 0 through 9? Wouldn't that be drastically more efficient? You could pack way more information into a single wire.
You're absolutely right. It would be vastly more information dense. But we don't use binary for storage efficiency. We use binary purely for reliability. It directly goes back to the noise problem we talked about earlier.
Oh, so?
Imagine we actually tried to build a decimal-based computer chip. We're using a microscopic wire carrying a maximum of 3.3 volts. We would have to divide that tiny 3.3 volts into 10 distinct recognizable levels.
Okay.
So 0.3 volts perfectly represents 1.6 volts is the 2, 0.9 volts is the 3, and so on up the ladder.
The steps between the numbers are tiny.
They're completely minuscule. Now imagine a tiny real-world fluctuation in the power supply. The ambient room temperature changes, or maybe a laptop battery gets slightly low. The voltage on the wire randomly dips by just 0.2 volts.
Right.
Suddenly your crisp 3 physically looks exactly like a 2 to the processor. Oh, wow. Your bank account balance just drastically changed simply because it got hot outside.
That is a total nightmare scenario.
It's completely unusable at scale. By stubbornly using binary avoiding, we create a massive, practically foolproof safety margin. We confidently declare that 0 volts is a 0 and a full 3 volts is a 1. You could have a massive spike of interference, a whole entire volt of random static, and the computer will look at 2 volts and still confidently say, well, it's definitely not 0, so it absolutely must be a 1.
So computers actually are inherently smart. They're just incredibly paranoid about making mathematical mistakes.
They are aggressively robust by design. And because the physical switch itself is so structurally simple, just purely on or purely off, we can manufacture them to be incredibly, incredibly small.
And when we say small, we mean nanometer small now.
Yes, the absolute bleeding-edge current generation of processing chips uses transistors with physical features as small as 3 nanometers across.
The research pointed out that a standard rhinovirus, the virus that causes the common cold, is roughly 30 nanometers across.
So we are mass manufacturing Billions of functional electronic switches that are literally 1/10 the physical size of a virus. And we're packing roughly 25 billion of them onto a single flat slice of silicon that is about the size of your thumbnail.
That specific scale is just, it really breaks my brain a little bit to try and visualize. And we use these billions of interconnected switches to build computer memory.
Yes, we arrange these tiny transistors into highly complex architectural patterns to safely store all those Ds and the ones.
The notes strongly distinguish between SRAM, DRAM, and flash memory. I really want to touch on DRAM first because that's the literal RAM we always talk about buying for our computers. The research calls it the leaky bucket design.
Right. DRAM, or dynamic RAM, is incredibly cheap to make and very dense. It brilliantly uses just one single transistor and one single microscopic capacitor to store one bit of data. The capacitor is essentially a tiny temporary bucket for holding electrons. If the bucket is totally full of electrons, it registers as a 1. If it's completely empty, it's a 0.
But those microscopic capacitors aren't perfect, right?
No, they leak terribly. The trapped electrons slowly drain out through the silicon. If you just fill it and leave it alone, your saved 1 will spontaneously turn into a 0 in just a tiny fraction of a second.
So the computer hardware has to constantly babysit the memory.
It has to aggressively refresh the memory, literally thousands of times every single second. The memory controller rapidly reads every single bucket, sees that it's half full, and violently tops it back up to full. That's precisely why it's called dynamic memory. It has to be constantly electrically active just to remember anything at all.
And that's exactly why when I pull the physical power plug on my desktop PC, I instantly lose every single unsaved document in my RAM. The babysitter turns off, the buckets leak out, and the data is permanently gone.
Contrast that fragile system directly with flash memory.
Yeah.
Like what's inside your USB thumb drive or your laptop's SSD. That uses a totally different design called a floating gate transistor. It effectively has a microscopic trapdoor built in.
Okay.
Using high voltage, we aggressively push the electrons through the trapdoor into a tiny holding chamber that is heavily surrounded by a thick layer of physical insulation.
So they literally can't get out.
They're completely trapped in a cage. You can copy a file, unplug the USB drive, toss it in a desk drawer for 10 full years, and those specific trapped electrons will still be sitting right there in that exact cage, patiently representing your family photos.
It's honestly amazing. We have completely mastered raw matter to the strict point where we can selectively trap isolated electrons in a microscopic box for a decade just to remember a picture.
It really is a triumph of engineering.
So we've officially reached the end of the stack. We've got all the way from the plasma in the upper ionosphere way down to the 3-nanometer silicon gate. I want to try to actively synthesize all of this. Let's trace the complete life cycle of a single message.
Oh, let's do it. A full trip through the infrastructure.
Okay, so I am sending a text message to you, just the word hello.
Okay, step 1. You physically tap the glass of your smartphone screen. That is an inherently analog event. Your physical finger hits a specific X and Y coordinate on the glass grid.
My phone's main processor, utilizing those 25 billion microscopic transistors, calculates that analog touch and converts it into the strict digital ASCII code for HELLO.
It temporarily stores those precise bits in the DRAM inside those tiny leaky buckets we talked about. Then the operating system prepares to send the message. It rapidly routes the binary data straight over to the cellular modem chip.
The modem then mathematically converts those digital zeros and ones back into a smooth analog radio wave, a high-frequency line-of-sight microwave signal.
The signal aggressively shoots out of your phone's internal antenna, flies directly across the physical street, dealing with attenuation along the way, and hits the local cell tower array.
The tower catches that weak wave. It instantly demodulates it back down into clean digital bits. But now it knows it needs to route it long distance to your city. It converts those electrical bits into intensely bright pulses of invisible laser light, exactly 1,550 nanometers.
It fires that laser light straight into a massive fiber optic bundle buried deep under the city street. The photon hits the internal glass wall, finds the exact critical angle, undergoes perfect, total internal reflection, and flawlessly bounces its way straight to the main backbone hub of the internet.
It physically travels hundreds of miles, maybe gets routed through a massive complex switch in a windowless data center, and then gets pushed back out to another local cell tower somewhere near wherever you happen to be.
That destination tower converts the incoming laser light back into moving electrons and then back into a radiating radio wave.
It blasts it through the air to your specific phone. Your phone antenna catches the wave, mathematically checks for any injected noise, aggressively corrects any transmission errors, and finally lights up the exact specific pixels on your screen.
And I simply look down and read the word hello.
And that entire globally spanning process happened in what, like 200 milliseconds?
Literally faster than you can physically blink your eyes.
It is exactly like a global nervous system. We have painstakingly built a planetary scale nervous system.
And it is entirely based on the impossibly simple concept of a dumb switch.
Mm.
On or off, yes or no, 1 or 0.
So I really want to leave the listener with this final provocative thought I found in our research notes. We mentioned earlier that our current transistors are now roughly 3 nanometers wide.
Yes, incredibly tiny.
The actual physical gap between individual atoms in a silicon crystal is about 0.5 nanometers. We are quite literally running out of physical atoms to build these things with.
We are hitting the absolute hard wall of reality. When you get down to a scale that unimaginably small, classical Newtonian physics simply stops working, and quantum physics completely takes over. Electrons start doing impossible things. They start to, quote, tunnel. They can literally teleport across a physically closed microscopic switch.
So the off switch literally isn't off anymore.
Exactly. The leaky bucket basically becomes a complete sieve. We physically cannot shrink standard silicon transistors much further without the data corrupting itself instantly. Moore's law is rapidly hitting the ultimate atomic limit.
So the final question really is what comes next. If we physically can't make the silicon pipes any smaller, and we mathematically can't make the photons travel any faster than the speed of light, where does the information age actually go from here?
That right there is the literal trillion-dollar question in Silicon Valley. Are we looking at massive breakthroughs in quantum computing? Are we looking at strange biological computing? Or maybe optical computing, where the processor chip itself fundamentally calculates using beams of light instead of slow-moving electricity?
We really just don't know yet. But for now, the next time you glance down and see that little 4G or 5G icon sitting up in the corner of your phone, just maybe take a quick second to respect the absolute mountain of complex physics keeping it there.
Like we said at the beginning, it's not magic.
Yeah,
Honestly, it's significantly better than magic.
absolutely. Thanks for diving deep into the stack with us today.
Always my pleasure.
We will see you on the next deep dive.
You know, I was just sitting on the train this morning, just doing the usual commute.
Right.
And I'm streaming this 4K video. I'm answering a bunch of emails and tracking my location on a map all at the exact same time.
Yeah, just a normal Tuesday.
Exactly, just a normal Tuesday.
Yeah.
But I had this weird moment where I actually stopped and looked at the phone in my hand, and I just thought, this shouldn't work.
It really shouldn't.
I mean, the sheer number of things that have to go perfectly right just for this little plastic rectangle to function at all, it's basically statistical insanity.
It is. We call it technology, so we feel comfortable with it, but at this point, it's closer to alchemy. We have quite literally tricked rocks into thinking.
Tricked rocks into thinking. I love that. That's the silicon, right?
Exactly. I mean, we take sand, we purify it, we blast it with highly focused light, and suddenly it can calculate the trajectory of a rocket or stream a cat video directly to your face.
It's wild.
But we aren't just going to talk about the silicon today.
Right. Today we're doing a deep dive into the invisible stack.
Yeah.
And I have to say, the source material we pulled for this is just fascinating. Because it doesn't just look at the phone as a product. It looks at the actual physics story, the fundamental reality that allows the phone to exist.
And the scale is just mind-bending.
It is. We are going to take you from the microscopic size of a virus, which is basically the size of a modern transistor, all the way to the massive cables lying at the bottom of the Atlantic Ocean. So our mission today is to unpack all that invisible infrastructure that you use every single day.
And the thing that really stands out when you look at all these sources together is how incredibly fragile this entire system is.
Yes, fragile.
We treat the internet like it's this magical cloud floating above us, like it's just in the air.
The cloud.
Right,
Yeah.
but it's not a cloud, it's a physical thing. It breaks, it requires massive amounts of power, it generates intense heat, and honestly, most of us have zero idea how the sausage is actually made.
And according to the research, it's kind of hitting a wall right now.
That's the core tension of this entire deep dive. We've had this amazing free ride for about 60 years, riding on the back of Moore's Law. And the sources we reviewed are basically screaming that the free ride is over.
So we are entering a totally new era.
We are. An era where the hardware of the physical world, meaning atoms, electrons, thermodynamics, is really struggling to keep up with the software of our desires.
So for everyone listening, we've got a massive stack of notes here, and we're going to organize this into 4 clear pillars. First is the engine of speed, which is Moore's Law.
The engine of growth.
Right. Second is the capture of reality, which covers sampling rates and bit depth, basically how we turn the real world into code.
Yep.
Third is the global grid, that's mobile networks and the physics of radio waves. And finally, the map, which is how the internet actually routes your data across the entire planet. LAN versus WAN.
It's the invisible infrastructure of modern life.
Let's just dive right into the engine. Gordon Moore, 1965.
1965, the year it all really fundamentally changed. Gordon Moore, who would later go on to co-found Intel, made this observation. And it's important to clarify that it wasn't a strict law of physics like gravity or thermodynamics.
It was more of an empirical observation,
Yeah,
right?
exactly. He just looked at the trends and noticed that the number of transistors you could fit on a microchip was doubling roughly every 2 years.
And crucially, and this is the part that blows my mind, the cost of manufacturing those chips remained basically the same.
That right there is the economic miracle of our lifetime. It is the only industry in human history where the underlying product gets twice as good every 2 years for the exact same price.
It's hard to even wrap your head around.
Think about it with cars. Imagine if you bought a car and then 2 years later, for the exact same amount of money, you could buy a car that went twice as fast, got twice the gas mileage, and was half the physical size.
And then 2 years later, it doubles again?
Right. And this compounding doubling happened for 50 straight years. It totally democratized technology. It made it globally accessible instead of just being a luxury for the absolute elite. It drove the explosion of AI video games, modern medicine, telecommunications, all of it.
But let's unpack the actual how here.
Yeah.
Because the research gets into the modern manufacturing process, and honestly, it sounds like pure science fiction. We aren't just sitting there soldering tiny little wires together.
No, definitely not. If you want to understand why the phone in your pocket is so incredibly powerful, you have to understand a process called photolithography.
Photolithography.
Yeah, it's essentially printing with light. You start with a raw silicon wafer, you coat it in a light-sensitive chemical, and then you shine a light through a microscopic stencil, they call it a mask, to literally draw the circuit onto the silicon.
But the circuits they're making now are so unbelievably small, we're talking nanometers, that regular visible light is actually too fat to draw them.
Too fat. That's a great way to put it. It's like trying to draw a highly detailed miniature portrait using a giant fat permanent marker. You just can't get the fine details. The light waves themselves are too big.
So what did the industry do?
They had to move to something called extreme ultraviolet light, or EUV. And the machines that do this, they're made by a company called ASML in the Netherlands. They are arguably the most complex machines human beings have ever constructed.
And I was reading about these in the sources, and my jaw dropped. Tell them how they generate this EUV light.
Okay, so inside a vacuum, they drop a microscopic droplet of molten tin.
Just a tiny drop of tin falling through the air.
Right. And while it is falling in midair, they blast it with a high-powered laser. Twice. The first blast flattens it like a pancake, and the second blast vaporizes it, turning it into a plasma. And that glowing plasma emits the extreme ultraviolet light.
And they do this how many times a second?
50,000 times a second.
50,000 drops of tin blasted by lasers every single second, just to make the light.
Yes. And that process creates a light with a wavelength of exactly 13.5 nanometers. That incredibly fine light is the only way we can print modern computer chips with transistors that are just 2 or 3 nanometers wide.
Just to contextualize, that 3 nanometers for you listening right now, it is smaller than a single strand of human DNA.
It is smaller than a virus.
We are building billions of tiny logic gates smaller than a virus.
We're bordering right on the atomic scale at this point, and this leads to some benchmark numbers in the research that just completely break your brain. If you look at 1971, the Intel 4004 processor contained 2,300 transistors.
2,300.
Which was a lot back then. But today, a high-end processor in a modern device contains over 100 billion transistors.
From 2,300 to 100 billion. It's unfathomable.
But here is the major catch, and this is where our deep dive gets into the current crisis. We still call it Moore's Law, but strictly speaking, the frequency, the actual clock speed of the chips, stopped doubling a long time ago.
That's right.
Yeah.
I remember back in the early 2000s, marketing was all about gigahertz. You had a 1 gigahertz processor, then 2 gigahertz, then 3 gigahertz, and then it just kind of abruptly stopped around 3 or 4. We aren't walking around with 20 gigahertz computers today.
We hit what engineers call the thermal wall right around 2005. The research highlights this as a massive pivot point for the whole industry. As you pack these microscopic transistors closer and closer together and force them to run faster and faster, they generate heat.
So much heat.
If we had kept increasing the clock speed at the historical rate of Moore's law, the chip would have literally melted through your desk. It would have reached the temperature of the surface of the sun.
So physics basically stepped in and said no.
Exactly. The laws of thermodynamics called a timeout. So the engineers had to get clever. They realized they couldn't make the single brain any faster, so they just started adding more brains.
Right, multi-core processing.
Yes. Instead of having one guy working at super speed generating a ton of heat, you hire 4 or 8 or 16 guys working at normal speed. That was the first really big architectural shift. But now we are in the middle of a second massive shift, which is the rise of the GPU.
The graphics processing unit.
Hmm.
Which is deeply ironic because those were originally just built for playing video games.
Totally. They were specifically designed for rendering 3D polygons in games like Quake and Doom. But it turns out the math you need to draw a 3D monster on a screen, which involves doing thousands of relatively simple calculations all at the exact same time, is the exact same math you need for artificial intelligence.
And this is why NVIDIA is suddenly one of the most valuable companies on the entire planet. Their chips weren't initially designed to run an operating system like Windows. They were designed for parallel processing, which is perfect for neural networks.
Precisely. Moore's law regarding raw transistor density is severely slowing down because of physical limits. We are literally running out of atoms. You can't make a transistor smaller than an atom, so the growth has shifted away from just shrinking things and moved into changing the architecture entirely.
Like 3D stacking.
Right, 3D chips. Specialized AI cores. We are building massive skyscrapers on the chip instead of just sprawling single-story suburbs.
And the economics of this transition are wild. We mentioned earlier that the cost of the individual chip stays relatively low, but the cost of the factory, the fab that makes them, has just exploded.
It's a phenomenon known as Rock's law. It's a paradox where the price of the final chip stays flat, but the cost of the equipment required to manufacture that chip doubles every 4 years. A modern leading-edge fab costs upwards of $20 billion just to build.
$20 billion for one factory. That is the GDP of a small country.
It creates a nearly insurmountable barrier to entry. That's why there are only 2 or 3 companies in the entire world that can actually manufacture the most advanced chips. You have TSMC in Taiwan, Samsung in Korea, and Intel trying desperately to catch up.
Which turns the global supply chain into a massive geopolitical choke point. And staying perfectly impartial here, both left and right-wing political analysts agree this is a major vulnerability. We have all this invisible infrastructure heavily concentrated in just a few locations.
If one major factory in Taiwan goes offline, for whatever reason, the entire global economy catches a cold.
Or have a full-on heart attack.
Right.
So that is the engine. We have these silicon brains that are incredibly dense, incredibly hot, and pushing the absolute limits of material physics.
Yeah.
But a brain in a jar is totally useless if it doesn't know what the outside world actually looks like.
Right. It needs input.
And we live in a real world of smooth, continuous waves. Sound like color. But computers only live in a world of jagged, rigid steps, ones and zeros.
This is the fundamental problem of capture. How exactly do you digitize reality?
And that brings us to our second pillar, sample rate and bit depth. I feel like almost everyone has seen the term sample rate usually is 44.1 kilohertz on their music files, but most people have no idea what it actually means.
Think of our reality as a continuous flowing curve. A sound wave traveling through the air is a smooth, unbroken line. But to get that smooth line into a digital computer, we have to slice it up. We have to take quick snapshots.
Right.
So sample rate represents the x-axis. It's time. It's asking the question, how many times per second are we taking a measurement of this wave?
The analogy from the notes that really helped me is the movie camera.
That's a great one. If you take one photograph of a running horse every hour, you aren't capturing the motion at all. It's just a bad representation. But if you take 1,000 photographs every second and play them back, your eye is completely tricked into seeing smooth, fluid motion.
And audio works the exact same way. If we take enough tiny snapshots of the sound wave, our ear is tricked into hearing a smooth, continuous tone.
Exactly. More samples equal higher fidelity to the original analog wave.
But the magic number for audio is 44,100 times per second. Why that specific number? I mean, why not an even 40,000? Or 50,000?
It comes down to the science of human hearing and a guy named Nyquist. The Nyquist theorem is a mathematical rule that states if you want to perfectly reproduce a specific sound frequency, You have to sample it at a rate that is at least double its maximum speed.
Okay, so double the highest frequency.
Right. And human biology dictates that our hearing tops out at roughly 20,000 hertz. That's that extremely high-pitched whine that usually only teenagers can hear.
About the dog whistle frequency.
Yeah. So to accurately capture that 20,000 hertz sound, the math says we need to sample at least 40,000 times per second.
But the standard is 44.1. What about the extra 4,100?
That acts as a buffer zone. It allows engineers to use roll-off filters so the high frequencies don't distort and break the audio equipment. So 44.1 kilohertz became the absolute gold standard for CDs because it perfectly covers everything a human being can physically hear, plus a safety net.
And we can contrast that with standard telephony. A traditional phone call only uses about 8,000 hertz for its sample rate. Which makes sense, right? 8,000 is plenty to understand the words someone is saying, but it's terrible if you want to listen to a symphony.
Exactly. But here is a really big caveat that the research highlights. Sample rate is only half of the story. That just handles the timing of the snapshots. We also need to measure the actual volume or the intensity of that wave at each snapshot.
Right, so if sample rate is the x-axis, this is the y-axis. This is bit depth. And I think this is where digital audio gets wildly misunderstood by people.
So if sample rate is how often we look at the wave pick depth, is how accurate our ruler is when we measure how tall it is.
That is a perfect analogy, the accuracy of the ruler.
Imagine you are measuring the height of an ocean wave. If you have a really basic ruler that only has 2 markings on it, high and low, that would be 1-bit audio. It would just sound like horrific static because you are rounding off the subtle curve of the wave significantly.
You're basically turning a smooth curve into a blocky square.
Exactly. Now, standard CD audio uses a 16-bit ruler. That means your ruler has 65,536 individual little markings on it. Every single time you take a snapshot, you assign the volume to one of those 65,000 discrete levels.
Which sounds like a massive amount of detail.
It really is. It gives you a dynamic range of about 96 decibels. That means the difference between the absolute quietest sound you can record and the loudest sound before distortion is massive. The noise floor, that underlying background hiss, is pushed down so low that human ears literally can't perceive it.
But when you look at the professional audio world, like the audio they use when recording big Hollywood movies, they don't use 16-bit. They use 24-bit.
24-bit is a whole different beast. It gives you over 16 million unique levels of loudness on your ruler.
16 million versus 65,000. That is an enormous exponential jump.
It is. Now, for just casually listening to a song, you as a consumer probably can't hear the difference between 16 and 24-bit. But for the people editing the audio, it is absolutely crucial.
Because it gives them headroom.
Exactly. It allows a sound engineer to record a faint whisper and a massive gunshot in the exact same audio take. And the whisper won't be lost in the static hiss, and the gunshot won't clip and distort the microphone.
So when audiophiles talk about high-res audio, what we're really talking about is just a much finer mathematical grid. We have more slices in time with the sample rate, and we have much finer markings on our ruler with the bit depth.
Yes, but there's always a physical trade-off, and that trade-off is data size. A raw, uncompressed CD file is huge. It takes up about 10 megabytes of data for every minute of audio. Back in the early days of the internet over dial-up, that was completely impossible to stream.
Enter the MP3.
The MP3 format is basically the dark art of throwing things away. It uses something called perceptual coding. An MP3 algorithm looks at the raw audio file and says, okay, there's a really loud cymbal crash right here. And human biology means the ear literally cannot hear the quiet bass guitar note playing right after that crash because the ear is temporarily stunned.
So the algorithm just deletes the bass note.
It just deletes it. It throws the data in the trash. It's tricking the brain by exploiting the biological weaknesses of human hearing.
That's lossy compression.
Right. It permanently removes the data you probably wouldn't hear anyway to make the file small enough to download. But now, today, with 5G networks and fiber optic lines, we are finally moving back to lossless audio. We finally have the bandwidth where we don't have to throw data away anymore.
Which honestly is a perfect transition into our third pillar. We've taken all this reality and converted it into massive, high-fidelity digital data, but now we need to actually move it around. And we aren't just sending it through a wire, we are blasting it through the thin air. Let's talk about the mobile network.
A global grid.
The research on this section really clarifies something that I think confuses almost everybody, the actual difference between low-band and high-band radio frequencies. Like, why does an AM radio station travel for 50 miles, but my super-fast 5G connection completely drops out if I just walk behind a large tree?
It all comes down to the physics of the wavelength. Imagine a physical wave out in the ocean. A low-frequency wave is a massive, long, rolling swell. It can effortlessly wrap around islands. It can easily push through narrow gaps in rocks. That is exactly how low-band radio works, like your standard 700 megahertz cell signal.
So it travels really far and it punches right through the walls of your house.
Exactly. But there's a catch. Because that wave is so incredibly long and slow, it simply can't carry a lot of complex information. Think of it like a very slow conveyor belt. You can put a simple voice call on it, maybe a text message or a basic web page, but you absolutely cannot put a 4K movie on it.
Okay, so to get those crazy download speeds, we need high frequency.
High frequency, like the new millimeter wave 5G networks is completely different. It's not a rolling ocean swell. It's like a rapid fire machine gun ripple on a pond. The individual waves are tiny and extremely close together.
And because there are so many of them packed together, you can pack a massive amount of data onto them.
You can stream multiple gigabits per second. It's insanely fast.
But the downside is what?
The downside is they are incredibly fragile. A high-frequency radio wave is easily stopped by physical objects. A tree, a brick wall, heavy rain, even the oxygen in the air itself slowly absorbs the energy of the wave.
And this explains why the massive 5G rollout has been so complicated and ridiculously expensive. Because back with 3G or 4G, a telecom company could just build one giant tower on top of a hill and provide coverage for an entire town.
Right, but with high-band 5G, you can't do that. You need a small cell node basically bolted to a street lamp on every single street corner. You need a direct, uninterrupted line of sight to the phone. We are having to build a significantly denser physical infrastructure just to combat the natural physics of high-frequency waves.
And building all this brings up a concept from the notes that I found while the spectrum auction. Government's literally selling off the rights to use these invisible frequencies. It's essentially invisible real estate.
It's arguably the most expensive real estate in the world. Telecom operators pay billions, literally tens of billions of dollars just for the exclusive legal right to use a specific tiny slice of the airwaves.
It's just air.
But it's highly regulated air. If you tune your car radio to 98.5 FM, you hear a specific station purely because that company bought the rights to that exact frequency in your city. If you set up a transmitter in your backyard and try to broadcast on 98.5, you will get a knock on the door and you will go to jail.
It is wild to think about the empty air around us being parceled out and sold off like plots of land.
But it absolutely has to be. If everyone tried to broadcast their data on the exact same frequency at the same time, it would just cancel out into pure static noise. The electromagnetic spectrum is a finite natural resource. That's why engineers have to get so incredibly efficient with how they pack data into it.
Speaking of that organization, let's talk about the cell and cell phone. I think most people just assume a cell tower acts like a giant light bulb, just blasting a signal equally in a big circle.
It's much more organized than that. The network divides a geographical territory into zones called cells, and the base transceiver station, the actual antennas on the tower, usually divides its coverage area into sectors. Picture it like 3 separate slices of a pie. And the really clever part is that the network actively uses slightly different frequencies and adjacent cells to prevent them from interfering with each other. It's a massive shifting mathematical puzzle. At the center of it all is the core network, which acts as the brain handling authentication, checking who you are and routing, figuring out who you're trying to call.
And the part of this puzzle that always impresses me the most is the handover. I'm driving down the highway at 70 miles per hour. I'm talking on a phone call. I am physically moving rapidly away from one tower and hurtling towards another tower.
And your call doesn't drop. This is a highly synchronized dance. Your phone isn't just passively listening, it is constantly actively monitoring the signal strength of the tower you are currently connected to, while also scanning all the other towers around you.
It's always looking for a better connection.
Right. It reports all this data back to the core network multiple times a second. When the signal from Tower A drops below a specific critical threshold and the network sees that Tower B is now much stronger, it coordinates a seamless handoff.
And this all happens in milliseconds, right?
Literally milliseconds. The core network essentially shouts down the wire, okay, Tower B, get ready to catch this incoming user. Tower A, let go of them, right in WAWE. And your entire stream of voice packets is rerouted instantly. You never even hear a blip.
Unless, of course, the call drops, which happens to all of us.
Which happens when that complex negotiation fails, or you drive into a dead zone where there simply is no Tower B to catch you. Or if you leave the country entirely and rely on roaming, where your provider has to negotiate commercial agreements with foreign towers just to let you connect.
Now, we've talked about the incredible speed of 5G, but the source material really emphasizes latency as the true game changer here, the actual delay in the signal.
Latency is reaction time. It's the gap between cause and effect. On a standard 4G network, the latency might be 50 to maybe 100 milliseconds.
Which to a human feels instantaneous.
Right. It's perfectly fast enough for us. We don't notice a 50 millisecond delay on a voice call or streaming a video. But for a machine, 100 milliseconds is an absolute eternity.
The classic example from the notes is the self-driving car.
Exactly. If an autonomous car is moving at highway speeds and a child runs into the road, that car needs to talk to the traffic grid or to the cars around it to coordinate an avoidance maneuver. In that scenario, a 100 millisecond delay in the network is the difference between life and death. The car travels several feet in that tiny fraction of a second.
So the goal of 5G isn't really just about letting me download a movie faster.
5G aims for 1 single millisecond of latency. It fundamentally allows machines to react to each other in real time.
So 5G isn't really for us, it's for the robots.
In many ways, yes. It's the foundational nervous system for the Internet of Things. It's for automated factories, smart grids, and autonomous fleets.
Now, we absolutely cannot talk about the global grid without mentioning the massive new player sitting up in the sky, satellites, specifically constellations like Starlink.
Right. This changes the network geometry entirely. Traditional communication satellites, the ones we've used for decades for satellite TV or weather data, they sit way out in geostationary orbit. They are 35,000 kilometers above the Earth.
Which means the physical radio signal takes a comparatively long time to travel all the way up there and all the way back down. High latency.
Terrible latency. It takes hundreds of milliseconds. It makes playing a fast-paced online video game or having a snappy Zoom call virtually impossible. The delay makes people talk over each other.
But the new low Earth orbit satellites, the LEOs, like Starlink, they're only sitting about 500 kilometers up.
That is 70 times closer to the ground than a geostationary satellite.
So the latency is drastically reduced. It's almost as good as a physical cable in the ground.
It is, but the extreme engineering challenge is that because they are orbiting so close to the Earth, they have to orbit incredibly fast just to stay up there. They are just whizzing across the sky.
So a standard satellite dish on your roof won't work because it can't move fast enough to point at them.
Right, you don't just point a static dish. You need a complex phased array antenna that can electronically track multiple satellites as they fly by at 17,000 miles per hour, handing off your connection from one satellite to the next every few minutes.
It's the highway handover problem we just talked about, but happening in outer space at hypersonic speeds.
Exactly. It's an absolute marvel of modern engineering, and it is completely untethering us, bringing high-speed, low-latency internet to a ship in the middle of the Pacific Ocean or a research base in the middle of the Sahara Desert where you could obviously never run a fiber optic cable.
Okay, so we have digitized our reality. We've connected our devices to the radio grid on the ground and in space. But once my data packet leaves the cell tower, where does it actually go?
Now we need a map.
Right. This brings us to the fourth and final pillar of the deep dive, the map of the internet. Land versus WAN, and how the internet actually physically finds what you are looking for.
The easiest way to think about this is the fundamental difference between your private house and the public international highway.
Let's start inside the house, the LAN, the local area network. This is basically just my home Wi-Fi router, right?
Yes. Your home LAN is your own private digital kingdom. Everything inside it operates locally at very high speeds. Your router is the boss, and it hands out a local IP address to every single device in your house.
These usually start with 192.168, right?
Exactly. Those are private identifying numbers. They literally do not exist on the public internet.
So if I try to send a print job to 192.168.1.5 from my laptop inside my house, it goes straight to my printer.
But if I type that exact same number into my computer at my house, it goes to my printer, not yours. It's exactly like dialing extension 101 in a giant office building. It only works inside that specific building.
So how do we actually get out of the building? How do we transition from the local area network, the LAN,
Yeah.
out onto the wide area network, the WAN?
Your router sits at the border and performs a very clever magic trick called NAT network address translation. Right. It takes your private request from your laptop, stamps its own single public IP address on it, and sends it out onto the public internet. When the data comes back, the router checks its internal ledger and says, oh, right, this YouTube video packet was requested by the iPad in the kitchen, not the TV in the living room. And it forwards it to the right place.
It's acting like a digital bouncer at the door.
It's a firewall.
Hmm.
Without NAT, every single smart device in your house, your laptop, your phone, your smart fridge, would be directly exposed to the chaos of the public internet. Hackers could walk right into your network.
Now, here's the part of the whole routing process that I think is the biggest missing link for most people. The translation from words to numbers. I open a browser and I type in google.com. How does the global internet know where google.com actually is?
Because computers do not speak English.
Right.
They don't know what a Google is or an Amazon is. They only understand numbers. They only route traffic to IP addresses. The system that bridges that gap is called DNS, the domain name system.
A phone book of the internet.
It is the ultimate global phone book. When you type google.com and hit enter, your computer secretly sends a rapid background message to a DNS server. Usually this is run by your internet service provider or a massive infrastructure company like Cloudflare.
It asks the server, hey, where is google.com located?
And the DNS server replies instantly. Google.com is located at 142.250.190.46.
And then my computer finally drives the data packets to that specific numerical address.
Exactly. And you have to realize this lookup process happens for every single image, every hidden tracking script, every single page you load. It happens thousands and thousands of times a day just for one person.
And if that system breaks?
If DNS goes down, the internet effectively disappears for the average user.
We've actually seen that happen a few times. Massive global outages, simply because one major DNS provider had a software glitch.
Right, the websites themselves are still perfectly fine, the physical cables are fine, but the map is gone. You simply can't find anything unless you have the IP addresses memorized. It really exposes how highly centralized some aspects of this supposedly decentralized network actually are.
So the request leaves my house, gets the proper numeric address from the DNS server, and then hits the main global backbone. And this is where the physical reality of the internet gets incredibly cool. We always visualize the internet as satellites and wireless signals beaming through the clouds, but the backbone is mostly underwater.
It is 99% underwater. Submarine cables crossing the oceans.
When I first visualized these, I pictured giant metal pipes the size of a subway tunnel.
A lot of people do, but the cable itself is remarkably thin. It's usually about the thickness of a standard garden hose.
The garden hose, connecting entire continents.
Yeah, and inside that garden hose, you have these delicate, hair-thin strands of ultra-pure glass. The fiber optics. The data travels through those glass strands as pulses of light bounding across the ocean floor.
And these cables are literally just laying exposed on the bottom of the ocean.
For the vast majority of the journey, yes. When they get close to the shore in shallow water, they bury them in trenches to protect them from things like dropping anchors and commercial fishing nets. But out in the deep abyss of the open ocean, they just unspool them off the back of a ship and let them sit directly on the seabed.
I read this detail in the notes that actually made me laugh out loud. Sharks used to bite the internet.
They did. Back in the early days of fiber optics, sharks were actually chewing on the cables. Scientists think the electromagnetic field generated by the amplifiers on the cable confused the sensors in the shark snouts, making them think the cable was a struggling fish.
So how did they fix it?
They had to go back and start physically shielding the deep-sea cables with layers of Kevlar and steel mesh just to make them shark-proof.
But the bigger threat to the network isn't sharks, it's human error. It's boat anchors.
Ships dragging their anchors in shallow water are the absolute #1 cause of internet blackouts globally. A large cargo ship accidentally drags its anchor, snags a cable, snaps it in half, and suddenly an entire country loses 50% of its internet bandwidth in a single second. It happens way more often than you'd think.
And then there's the spy angle, the geopolitical side of the submarine cables.
Well, it's simple logic. If you physically control the cable, you control the flow of information. During the Cold War, the U.S. Navy famously used submarines to physically tap into underwater Soviet communication cables.
Right, and staying completely impartial to the politics of it today, there's a massive ongoing struggle between nations over who exactly gets to manufacture and lay these new cables.
Is it an American tech giant? Is it a state-backed Chinese telecommunications company? Because whoever builds and maintains the physical infrastructure theoretically holds the keys to silently listen in on the data traffic.
It's the modern equivalent of a strategic trade route. Instead of galleons carrying spices and silk, it's garden hoses carrying the world's financial data and military communications.
And just like the old trade routes, they require protection. Navies actively patrol the areas where these cables surface. It is considered a Tier 1 critical strategic asset for any modern nation.
So let's zoom out and synthesize everything we've covered today. Because when you stack it all together, we have built an almost incomprehensible machine. We start with the microscopic transistor manipulating individual atoms to create digital logic, constantly fighting against immense heat and quantum tunneling. We use mathematical sampling to slice analog reality into billions of discrete bits, fighting to capture the true fidelity of the physical world. We build massive mobile networks to blast that data through the thin air, fighting against the harsh physics of radio waves and environmental interference. And finally, we lay thousands of miles of glass cables under the crushing pressure of the oceans, fighting against the raw geography of the planet itself.
It's quite literally a layered miracle. Every time you send an emoji, you are activating billions of dollars of infrastructure across the globe.
But let's bring it back to where we started this deep dive, the fragility of the whole system and the rapidly approaching physical limit.
Right, the provocative thought we promised.
Because Moore's law is undeniably slowing down. We are finally hitting the hard physical limits of silicon and thermodynamics. We simply cannot make these transistors smaller forever. The atoms won't allow it. But our demand as a society, our demand for data is completely exponential.
It's a collision course.
We want immersive VR. We want AI models that can generate 4K movies on the fly. We want millions of self-driving cars communicating with each other in single milliseconds.
We are entering a new kind of resource crisis. Not a crisis for oil or fresh water, but a global crisis for compute power and physical bandwidth.
The software, the limitless bounds of human imagination, is completely outpacing the physical hardware that supports it.
And that reality creates a massive fork in the road for humanity. Either we discover a totally new technological paradigm like viable quantum computing or highly advanced biological computing, something radically different than silicon, or we're going to hit a plateau.
A hard ceiling.
A point where our technology simply stops feeling like infinite magic and starts feeling like a public utility that has completely maxed out its capacity.
It really feels like we are standing directly on that inflection point right now. The next 10 years of tech development aren't going to be about just giving us more of the exact same, but slightly faster.
Yeah.
It's going to have to be fundamentally different.
It has to be. And until we figure out what that next paradigm is, we just have to appreciate the current magic. The next time you are sitting on the train, just remember that the video you are passively watching is being mathematically sliced into tiny packets, routed via a global DNS phone book shot at the speed of light through a garden hose under the Atlantic Ocean, beamed to a cellular tower, and instantly reassembled on a glass screen that is refreshing 60 times a second, all powered by a silicon chip containing billions of microscopic switches smaller than a single virus.
When you put it like that, I suppose it's perfectly okay if the video buffers for a couple of seconds.
Yeah, give it a second. The machine is working incredibly hard for you.
Thanks to everyone for listening to this deep dive. Yeah. Hopefully you will never look at your smartphone or a shark the exact same way ever again.
Stay curious out there.
We'll see you on the next deep dive.